is Amber Trask, and I lead the community and education teams here at OpenMined. Today, we're going to dive into the details of how to get involved in OpenMined, no matter your location, background, or skill set. There's a place for everyone in our community, and I'm really excited to help you find yours. I'm going to start this session off with a brief presentation on who we are and how to get started within OpenMined, and then we'll hear 5-minute lightning presentations from many of our team leads about their specific teams, projects, and topics, and how to get involved in each team. This first presentation is loosely based on our welcome package, which is the best place to get started in our community. I've linked to the welcome package here, and it's also pinned to the top of our GitHub, so feel free to refer back to it later. Let's get started. First, I just want to kind of introduce you to who we are. One thing that's important to understand before we dive in is OpenMind's mission to align and incentivize all institutions to only serve the best interests of humanity. This means that we want to help you by both making your products and research better and protecting everyone's privacy along the way. At OpenMined, we strive to prove false the fallacy that in order for society to progress, we must sacrifice individual privacy. It's just not true. And we're here to create the world in which research, product, and personal privacy work hand in hand by educating anyone who wants to learn on how privacy-preserving tech can work for them and the world. As the community lead at OpenMined, it's my mission to cultivate a community for acquiring the skills necessary for anyone to be able to fulfill their personal goals in privacy-enhancing technology. That means that here at OpenMined, not only do we want to create the technology that keeps you private, but we also want to create a community where no matter your location or means, skill set or speciality, we can help you show up and become informed enough to select a valuable goal for yourself, receive tools along the way to help you achieve the next step, and reach a place where privacy-enhancing technology is sustainable for you full-time, inside or outside of OpenMined, no matter which industry you're in, whether it's development, legal, marketing, or any other field. We're here to make this happen for you because we want to start a revolution of privacy experts, advancing on the world to make it a better place for all of us. OpenMined is a global community of people who are passionate about privacy and are working to make the world more privacy-preserving by volunteering their time to our open source project. Check out our GitHub, linked here, to see what our community is working on. Here's a map showing the locations of our various team leads all over the world, and this just scratches the surface of how distributed and diverse our community really is. These team leads are people who specialize in topics ranging from natural language processing to design, cryptography to social media, federated learning to event planning, and much, much more. We'll hear from some of these folks later on in our lightning presentations, but in the meantime, let's briefly look at how our teams work. OpenMined is comprised of various teams, including the community, development, and research teams you see listed here. Check out the welcome package in our GitHub linked here for more specific details on each team. Before we dive into the best places to start contributing, we're going to start off by discussing the best ways to join the community. First things first, if you haven't joined our Slack organization, the link is just slack.openmind.org. If you're not familiar with Slack, it's just a chat app like AIM or MSN Messenger in the old days, and it's where most of our community and teams communicate and stay up to date with each other. This is absolutely the lifeblood of the OpenMined community, and it's thriving with over 8,800 members, so it's definitely the best place to get started. When you join the Slack organization, you will be automatically added to the starter channels that you see here. These names are fairly self-explanatory, but just a quick note that getting started is the best place to explore first. And if you click on the pinned posts in that channel, there's a ton of info to help you get started. There are many other channels for various topics, communities, libraries, educational resources, and locations, so feel free to explore the community by searching for some of the prefixes listed here. Also note that if you do want to get involved in our codebase, the best places to ask questions as you go are topic beginner questions and the library-specific channel for the code you're working on. The next best place to join our community would be with OpenMined Education. OpenMined Education is made up of our mentorship team and our learning team, and they're both here to help you set and reach your goals. The OpenMined community has put together a ton of resources to help you learn, but it's clear to us that not everyone learns in the same way. The mentorship team is here to give you one-on-one guidance as you decide on your goals and learn whatever it is that you need to achieve them. To join our mentorship program, just visit mentorship.openmind.org and fill out the form to receive guidance from one of OpenMind's mentors. Once you've filled out the form, you can also join the Slack channel, EDU Mentorship, where all of our mentors and mentees gather to get to know each other and ask questions. If you learn better in groups, that's what the learning team is here for. OpenMind's learning team puts together boot camps, study groups, and other learning initiatives of various sizes so that you can work together with other learners as well as seasoned members of the OpenMind community. To stay up to date on upcoming learning initiatives, just join the Slack channel EDU Learners. And if you're curious how past boot camps have gone, check out the boot camps repo in OpenMind's GitHub linked here. If, however, you prefer to dive right in and get to work on your own, the best place to get started is our welcome package. We're going to jump over and take a look at that now, as the welcome package includes links to introductory videos from our leader Andrew Trask, information about our free Secure and Private AI Udacity course, as well as links to all of OpenMind's library's tutorials, their good first issues, and tons of other great info. Let's hop over there now and check it out. This is OpenMind's welcome package. This is pinned to the top of OpenMind's GitHub, but the link is just here at the top for future reference. As you can see from the table of contents, we've already touched on some of the information you see here. So we're going to skip straight to the learning section where you can find the best resources to get started learning about OpenMind on your own. As I mentioned before, here we have a couple of introductory videos giving you a brief overview of what OpenMind does, and then there's information about our free Secure and Private AI Udacity course. This gives you the option for a quick overview of what OpenMind does or a deep dive. Next, we have links to our tutorials and good first issues for some of our bigger projects. If you'd like to jump straight into the code, this is the best place to get started. The tutorials you see here will teach you how to use each library, and the good first issues are the best place to try your hand and start contributing. The tutorials and good first issues are the best places to get started if you're interested in development, but there are a ton of teams within OpenMind, development and otherwise. So the next section in the welcome package includes the links for more information on all OpenMind teams. Once you know a bit about who we are, you may be ready to join a team based on your current skill set. We're going to check out the more detailed information about our teams momentarily, but before we dive in, I just wanted to show you placements.openmind.org. This placements page is where OpenMind's teams advertise for their volunteer positions. As you can see, many of our teams are looking for members, so this is a great place to check and see what might be the best fit for you. All of the placements here are volunteer positions unless noted otherwise. However, contributing team members are shortlisted for grant funding when it becomes available. So join a team first, and it's possible funding may be an option later. We'll hop back over to the welcome package now just to briefly show you the detailed team information, starting with our development teams. Here on the development teams page, we have a diagram showing which team does what, and then detailed information for each dev team, including links to the team's roadmap, good first issues to get started contributing to that team, and the requirements and link to apply to join the team. And if you scroll through, you'll find this information for each of our dev teams. This team information is constantly evolving, so keep checking the welcome package if you want to know more about the current state of OpenMind's teams. If you check out the community teams page, it serves largely the same function. Information about what each team does and the requirements and links to apply to join. And lastly, the research teams page, which goes over the research scientist and research engineer roles and how to join OpenMind research. So if you're passionate about privacy, we want to help you meet your goals, and I hope that so far I've been able to give you a taste of the variety of places that you can fit into our community. Here are a few more links to places to help you stay up to date with what's going on in OpenMind, and don't forget to join our Slack at slack.openmind.org and check out placements.openmind.org for opportunities to join one of our many teams. That wraps up my first presentation. Once again, my name is Amber, and please feel free to reach out to me anytime on Slack at 4MBER or email at amber@openmind.org. So now let's dive in and hear more from our team leads. This diagram illustrates how all of OpenMind's teams work together, and it's also found on the first page of the welcome package. We'll be coming back to this diagram as we hear from our team leads now, so I wanted to go ahead and introduce it to you to help you follow along. As you can see, many of our teams have sub-teams, which focus on more specific areas within their topic. The team leads are listed on this diagram, so feel free to reach out to any of them on Slack if you have questions about their team or topic. We're going to start our team presentations with some of our community teams. First up, we have Saurav Das, who leads our mentorship team. As you can see here, the mentorship team is an educational team with two sub-teams, community and technical mentors. Saurav is joining us from Assam, India. Take it away, Saurav.
Hello everyone, my name is Saurabh. I lead the mentorship team at OpenMined. Hope you all are enjoying the privacy conference and learning a lot about privacy using AI. Alright, I'm going to share my screen. So today I'll be talking about the OpenMined mentorship team and the mentorship program, how we can apply for it, why should I apply for the mentorship program. I'll also share a few tips to graduate from the mentorship program, how you can join the team and joining the awesome community. So yeah, let's get started. OpenMind mentorship team is part of OpenMind education. We provide one-on-one mentorship in the community. We have 20 awesome mentors in our team, and we have mentored over 1,000 plus community members from all over the world. Mentors guides you to get started contributing to OpenMind. They guides you to your learning process, navigating the community, or joining the development, research, or community teams, and to become an awesome active member of the community. Here are the awesome mentors of the OpenMind mentorship team. They are super awesome. Applying mentorship is pretty easy. You just have to fill out the form visiting mentorship.openmind.org. Then you'll be assigned to an awesome OpenMind mentor, and he will guide you to get started. Well, why should you apply for the mentorship? Yeah, so if you are new to OpenMind and you don't know where to get started, you're confused about it, you want to learn privacy preserving AI, you are very new to OpenMind and you want to contribute to open source, and yeah, mentors are there to guide you. You want to join OpenMind teams and get involved in the community, or you want to learn about OpenMind projects, code base, or you want to prepare for a team host a meetup or anything else. Mentors are there. Mentors are the best people to guide you to get started and help you. So anyone can apply for the mentorship program. We are looking forward to everyone who apply for the mentorship to graduate from the mentorship program. Here are a few tips from me to graduate from the mentorship program. First of all, set a goal. First, your mentor will guide you for that. Have a conversation about your goals with your mentor. Stay in touch with your mentor. Feel free to ask a question in the community. Manage your time well and be consistent in your learning process and active in the community. Yeah, so do not give up. You got these mentors are there to help you, so don't worry. We are recruiting new mentors. If you wish to be an OpenMind mentor and lead the community members, fill out this form or message me in Slack. To be a part of the awesome community, it's very easy to join the Slack. We have over 8,800 members from all over the world. It's a very diverse and friendly community, so you can join the OpenMind community by going to openmind.slack.com. Yeah, so feel free to reach out to me if you have any questions. You can find me in Slack at Saurabh. I'm also pretty active in Twitter. You can also contact me there as well at the rate Adventurous SRV. So yeah, thank you, and keep making the world more privacy preserving.
Thanks, Saurav. That's awesome. Next, we'll be hearing from Yemi Kafuli, who leads our learning team, the other team that makes up OpenMind Education. As you can see here, our learning team consists of 3 sub-teams focusing on the various tasks that make up a learning team initiative. Yemi is joining us from Cotonou, Benin, Africa. Yemi?
Hello. Welcome to this presentation of the OpenMined Learning Team. I am Yami Kifuli, the person doing the presentation. I became interested in private AI a couple of years or so ago, and I joined OpenMined in 2019 and became a mentor, and I am now the lead of the learning team. And it's in that capacity that I'm here today doing this presentation of my team. The presentation is divided in 5 parts: who we are, what we do as a team, our beta bootcamp, what you should do if you want to learn with us, and how you can join the team. So, who we are. Well, the learning team is an open-mind education team, which means that our activities are geared towards teaching private AI and everything that OpenMined does. We are a group of volunteers, more than 50 volunteers with different skill sets and very different backgrounds, but we all share a passion for privacy preserving, machine learning, and the OpenMined mission, and we are all very eager to spread the message of private AI. What we do, well, generally speaking, our mission is to empower the advancement and adoption of privacy enhancing technologies by offering a high quality but low barrier to entry learning experience. And the way we achieve that is by organizing bootcamps. Our bootcamps are entirely online and completely free. They're short in duration, only a few weeks. And the topics go all the way from deep learning to privacy preserving machine learning and the OpenMined projects and software such as PySift and PyGrid. Our bootcamps are open to beginners, meaning people who are new to data science, and seasoned AI practitioners. So basically, we have bootcamps that are for people who are new to data science. So such bootcamps will be focused on introducing data science, introducing deep learning, and so on. And then we have other bootcamps that are to introduce privacy preserving machine learning or the more advanced AI topics. So we have several bootcamps to make sure that we are catering to a large group of people with different level and different background. During the bootcamp, we create engagement activities to keep participants on track and to help them network with other participants. And one of our biggest goal, in fact, is to help people take what they learn and use it in real life. And we help them do that by giving them the opportunity after the bootcamp, well, after the teaching part of the bootcamp, we give them the opportunity to work on a project that they can then present when the bootcamp is closing up. So that's what we do, and that's our goal. Our beta bootcamp. We just finished our beta bootcamp, which was our introductory bootcamp, our very first bootcamp ever. We had 15 participants. It ran from July 24th to September 12th, 2020, and covered the notebooks 1 through 8 of the PySafe tutorials. You can find those tutorials in the OpenMined GitHub repo, in one of the repos. The summary of the bootcamp: we had 3 people contribute to the OpenMined repos. We had 1 person write an article. We have more people who are currently working on projects still. They didn't get to finish them before the bootcamp closed. And when we have 15 more people in the world who know more and can do more with private AI, so that's good news. We are now working towards launching our very first regular bootcamp that will have a much larger cohort size, and the launch date will probably be in late October or early November 2020. What can you do if you want to learn with us? Well, the best way to learn with us is right now to keep up with the Edu Learners channel. It's in the OpenMined Slack workspace. You can join the channel and keep up with the announcements on that channel. Keep up with the announcements on the OpenMined social media platforms as well, because when the bootcamp will launch and the sign-up sheet will be shared for people to sign up for it. That's how we will announce it. So yeah, Right now, if you want to learn, the best way is to keep up with those platforms so that you get notified once we are ready to launch the bootcamp. If you want to contribute, we are really, really, really excited to have you in our team. We have roles for in for all people. Zero technical knowledge, some technical knowledge, lots of technical knowledge, because we have several sub teams in the learning team, and we have one for everyone. So if you're interested, if you're enthusiastic, if you want to help, you can use the form to apply. You can also find the form in the Edu Learners channel at the top, as is shown here on the screenshot there. And there it is. We will be really happy to have you in our team. That's about it for the presentation. I hope this helped you learn a little more about the learning team. Thank you for hanging out with me, and see you in Slack.
Nice. Thanks, Yemi. Next, we'll be hearing from Helena Barmer, who is currently leading our events team, which handles online meetups, paper sessions, helping the learning team with webinars, and planning many other OpenMined events. Helena is joining us from Malmo, Sweden. Helena?
Hi, my name is Helena Bormer, and I am part of the online events team at OpenMined, currently leading it. The online events team are helping with hosting, planning, and moderating online events throughout the community, which is very fun. You get to meet a lot of people, you get to help them to get a flow within your online events. At the moment, we're actually looking for someone to help leading the team. And if you have any experience with event planning, if you love organizing and meeting new people, you should definitely head over to placements.openmind.org to check it out. I hope to see all of you throughout this weekend, and I hope that I already met you maybe in one of the talks, and just have a really good time, enjoy the conference, and have a really good day. See you all.
Thanks, Helena. Next, we'll be hearing from Bennett Farkas, who leads our brand and marketing team. As you can see here, the brand and marketing team consists of our writing, design, and social media teams, some of which you'll hear from next. Bennett is joining us from Nashville, Tennessee. Take it away, Bennett.
Hey, everybody. As Amber mentioned, I'm Bennett Farkas. I lead the brand and marketing team here at OpenMined. I am based out of Nashville, Tennessee, and I've been contributing in some capacity to the OpenMined community since early 2017, I think. In my day job, I work as VP of Creative at a marketing firm called Golden Spiral here in Nashville that works with business-to-business technology companies, kind of bringing their stories to life for the market. Some of you might be directly familiar with my work within the OpenMined community. I was the design lead for the OpenMined logo that we're using today, as well as the person responsible for leading the creation of the OpenMined brand aesthetic in general, the fonts, colors, etc., as well as the logos for Grid, Sift, Opus, Ciphertext, 3PO, as well as the forthcoming logos for Premia, Duet, and Sift 3.0. With obviously so much collaboration from the super talented people we have here in the community. Right now, the brand and marketing team is comprised of 3 different team leads, as well as some kind of individual specialists. The 3 main team leads in this team are Emma, who heads up the writing team, and Madeline, who heads up the social media team. Both of them will give more specific information about their respective teams at some point in this same kind of presentation. And then also Kyoko, who's the newly appointed design team lead. So those are kind of the 3 team leads that are a part of this team, as well as Amel, who many of you are likely familiar with, but she facilitates and coordinates the OpenMined AMAs, and Josiah, who is working on developing some marketing analytics and insights for our marketing team. Our team will likely evolve over the next year. Nothing set in stone yet, but well, it will almost certainly definitely evolve, as everything in OpenMined does. But we will likely look to incorporate a website team and corresponding lead, a PR team and corresponding lead, as well as kind of a more filled out insights and analytics function and team to this group. On a high level, this team works to package and communicate what OpenMined is and does. As you can imagine, that's a fairly significant challenge, but we're making a lot of really good progress. We've made a lot of great progress specifically over the last 6 months. Our big projects over that time have been working to help form and communicate our core mission, vision, and values as a community. We've been working on the strategy and design for the OpenMined website 2.0, which is super fun and exciting. A lot of good progress being made there. Working on clarifying and supporting the OpenMined brand structure. What's a product, what's a team, what gets a logo, etc. Emma has been working with her massive writing team, crafting some incredible articles for our blog. Madeline is doing all the scheduling and posting for all of our social channels, doing a killer job on that, as well as facilitating the announcements channel in Slack. As I mentioned, Amel is facilitating the AMAs that we host. And lastly, our largest big project has been what has become the landfall of opportunity and tasks associated with facilitating this conference that we're all getting to attend now. So that's been a big priority over the last several months. Looking at the next 6 months, there are 2 primary objectives, likely subject to change, but the one that's not changing is we're going to look to launch the website 2.0, as well as we're working to craft a kind of cohesive strategy that effectively utilizes all the integrated teams and aligns them towards common goals. So those are the 2 main priorities for the next 6 months. Right now, we're looking to we're looking for all sorts of help. I'll let Madeline and Emma speak to their teams specifically, but I will say that if you're any kind of skilled graphic designer or illustrator, we could definitely use your help. So much of what's happening in our community is communicating really complex problems, and graphics and figures go a long way to help communicate that, as well as a lot of big lifts that need to happen around the website specifically. We're also interested in anybody that has experience as a front-end developer, that has worked with user experience and user interface designers in the past to kind of bring websites to life. So we're definitely looking for that. And other than that, if you're just generally a marketing inclined person that has cool ideas for what our community could be doing, we would love to help. So I know that the design team has a post up on the placement site, and if any of this other stuff you're interested in, feel free to reach out to me directly. I'm just at Bennett on Slack, at BENNETT, and that's where you can find me. All right, thanks everyone.
Thanks, Bennett. Next, we'll be hearing from Emma Bloomkey, who leads our writing team. Emma is joining us from Oxford, England. Emma?
Hey, I'm Emma. I'm a PhD student at the University of Oxford, and at OpenMined, I lead the writing team. The writing team is a group of almost 50 writers from all around the world with a variety of skill sets and interests. And today I'm here to talk to you about what we're working on, what we'd like to work on in the future, and how you can get involved. So, our writing team produces the material for our blog. That's at blog.openmind.org. You should go check it out after this, and I'm sure you'll find something that you like. We produce a huge variety of material. Some of it is purely writing, some of it is highly technical. For example, sometimes we are just announcing good news. We always have a lot of good news around the community, such as that OpenMined is officially listed as a digital public good by the UN now. And we always have partnerships that we have to announce. We always have fellowships, grants, and various community items that need to be written up and put on the blog. So if you like writing, that's a great place for you. So we also produce demonstrations of concepts or tricks that you can do relating to privacy. So for example, here's a demo of how to extract private data from a neural network. This is really, really useful for the community and really, really interesting material for everybody who follows us. We also write demonstrations of tools. So for example, these are code demonstrations like this one on how to use PySift, PyTorch, and Intel SGX. These are really useful to show people how to use our tools. We Also write about use cases for privacy tools. So maybe you're a domain expert in genetics or another area of healthcare, or maybe climate change, or maybe in financial services. Well, you can write a blog about why privacy tech is interesting to you and where you see that it could be used. And you can also write commentary about privacy-related stuff that's in the news. So, for example, this article on some huge news in the natural language processing area. We also welcome blogs about tech ethics and data ethics. For example, this recent piece about surveillance capitalism and whether or not privacy technology is a solution for some of the problems posed there. I would just like to point out that this is an open call. If you are a humanities researcher, STS researcher, political scientist, social scientist, please join us. We welcome your skill set, and we'd love to have your perspective on our blog. Not all of our blogs contain code. Some are writing only. So if you are not a coder, don't worry. There's a huge range of skill set that is needed in privacy. We also conduct interviews, such as this one with Ronnie Falcon, our OpenMined feature contributor for June. If this inspires you, you're very welcome to expand on this and interview perhaps people in the privacy space that you find interesting. Find out what they're working on and perhaps ask them about their journey. We also provide teaching material. One of the main goals of OpenMined is lowering the barrier to entry to privacy-preserving tech, and a huge part of that is explaining all of this stuff. So one of our popular series is this Privacy Preserving Data Science Explained series, and that is really just a branch for answering all the questions that people come to us with, like what is federated learning, what is private set intersection, what is PyVertical, what are these libraries that we're working on. So if you have an area of expertise or you're a beginner who likes to write blogs to kind of wrap their head around a topic, let us know and join us and help us expand that series to cover everything that we would like to know. You might also find our material reposted on the PyTorch Medium sometimes. So that's especially when we collaborate with PyTorch and do really cool demos demonstrating our tools. Okay, so you can find out information about how to join on our writing team roadmap. You can actually find all of our projects on OpenMind's GitHub. All you have to do is go to OpenMind's GitHub and click on projects, and you'll see, for example, this is our privacy teaching series. This is what we still have to write. This is what we have already written, and this is what's in progress. So I really hope that you come, you check out our good first issues, you maybe suggest new blog posts about what you guys would like to write. So I really am looking forward to seeing all the ideas that are sparked from this privacy conference. For all the details on how to apply, check out the roadmap.
Thank you, Emma. Up next, we have Madeline Mamulianu to tell us about the social media team. Madeline is joining us from Craiova, Romania. Madeline?
Hello everyone, my name is Madalin Mamuleanu. I'm from Romania and I'm leading the social media team at OpenMined. The social media team is formed by members of the OpenMined community passionate about content creation and building engagement by analyzing the impact of social media activity on the community initiatives. We are responsible for strategic development and execution of social media campaigns in order to increase engagement. Our main goal is to make sure we reach our target audience, research scientists, engineers, students, developers, or people interested in privacy in general when promoting OpenMined activities, achievements, or events on social media. For a better distribution and scheduling of our content, we've divided our social media channels into two main categories as you see in this slide. For external channels, we are using Twitter, LinkedIn, Facebook, YouTube, and our monthly newsletter. And for internal announcements, we are using Slack. We are promoting a large range of post types on social media, starting from partnership announcements to online events in the community, features added to a product, research results, meetups, to announcing monthly featured contributor or different types of blog posts like tutorials on different technologies. Also, we are using YouTube to schedule Ask Me Anything live events. Since on every platform the same posts are performing different, we always trying to adapt our message across each channel in order to reach our target audience. We think that by keeping all of our social media channels updated with OpenMined achievements, we encourage other people to join us in different teams. Our team works to create engaging content for OpenMined social media presence, both external and internal, as defined earlier. We are working closely with development, research, design, and writing teams so we can always be up to date with everything that's happening in our community. Also, we analyze data to measure engagement for each platform in order to have a better view of which type of content works better so we can adapt and improve our message. Since our community is growing really fast, we need more people to join our team. If you are interested in writing engaging posts for our community channels, analyze data to see which posts are working better for which platforms, or even both, and you want to join the social media team, please reach out to me on Slack, on email. We'll be really pleased to have you. Thank you for listening, and don't forget to follow us on social media.
Thanks, Madeline. So that wraps up our community team's presentations. Next, we'll hear about OpenMined research from Kritika Prakash. Kritika is joining us from Bangalore, India. Kritika?
Hello everyone, my name is Kritika and I'm going to be talking about the research happening at OpenMined. First, I'll tell you about the problems that we aim to solve, continued by the specific research areas of focus. Then I will give you an example of some of the research projects that are happening, and finally I'll talk about the different ways you can get involved with research at OpenMined. Over the broad fields of science, medicine, governance, technology, and capitalism, we want to solve people-centric problems using data-centric methods such as artificial intelligence, encrypted computation, distributed systems, and remote execution, with the aim of adding value to the lives of these people. And this value can be seen in the form of data transparency, the security and privacy of the people, the fairness in the way the data is being used, and so on. So, broadly speaking, this is what we're interested to solve in. Corresponding to the problems that we want to solve, our first step is to focus on creating a secure and private way of using artificial intelligence on people's data to make a difference. The key research areas that we're currently working on, which will enable the creation of secure and private AI, are federated learning, a distributed way of performing machine learning, differential privacy, a mathematical guarantee on the user's privacy, cryptography, a smart and interesting way to establish secure communication, and verifiable identity. Within artificial intelligence, our focus is on machine learning, deep learning, and natural language processing. Keeping these key research areas in mind, I will now move on to some examples of the research projects that are happening at OpenMined. Here is a small subset of the research projects that are taking place at OpenMined. As you can see, these research projects have a broad scope and are highly interdisciplinary. Whether we look at achieving transfer learning or neural architecture search in a federated learning setup, or we look at more general projects such as automating differential privacy for deep learning or making recommendation systems privacy preserving, all of these projects have an impact on people's lives and their data. Now, I'm going to be talking about the different research roles that you can apply for at OpenMined. So, as you can see, the pictures of all the different researchers at OpenMined form a very diverse and interactive community who collaborate on lots of research projects together to create a wonderful research environment. There are two main roles which you can apply for. One is the role of a research scientist if you have prior research experience, and the other is the role of a research engineer if you have more of a development and less of a research experience. To be able to apply to both of these positions, check out placements.openmind.org. To get involved more generally with research at OpenMind, you can always join the research channel in the OpenMind Slack. We hope you apply and join the research community at OpenMind. Thank you.
Thank you, Kritika. Next, we're going to hear from some of our development teams, starting with Ben Simkoff to tell us about overall OpenMind development. Ben is joining us from Willetton, Western Australia. Go ahead, Ben.
G'day everybody, I hope you're having an absolutely amazing time, amazing virtual PryCon experience, and hopefully it's been so amazing that you've decided you want to come and join the community. My name is Ben Simko, the Development Area Lead here at OpenMind, and I wanted to talk to you a little bit about how you can actually get involved. I think that one of the very unique things about OpenMind, and I've been with the community now for almost 2 years, is that you can achieve the impossible. You think about the sort of people that are in our community. We have researchers working on new technologies, new techniques that are just never been seen before. Obviously, private AI is a very, very new field, and the mission that they're working towards is just so world-changing, game-changing, and privacy as an industry is obviously the biggest growth industry in the world, and it will be for the next few years. Not only that is we have these amazing engineers that can help make these research papers and techniques a reality, and we work with the biggest tech companies in the world as well as industry. We work with we work with a lot of healthcare, institutions, universities, etc. Why would you actually want to join? Like, what do you get out of joining OpenMind? So let's talk about the typical experience of an OpenMind contributor. When you first arrive, our technical communities, our Slack channels, very, very, very welcoming. In fact, most new members get a mentor assigned to them, which are going to help them navigate the community. So you can learn a bunch of new skills. We're a sharing and education-based culture. So if you want to learn about Rust, if you want to learn about mobile apps, if you want to learn about computer vision, cloak inference, or any amazing, brand new privacy-preserving technique, we have the people here that are very, very willing to not only invest time to help you learn these skills, but then to bring you on board, and so you can start actually working with them in the project teams to build the libraries that can make these techniques a reality for not just the OpenMind community, but the entire world. The whole point of what we do is to make sure the entire world can get access to all of these tools that we build, so that the world can become a more privacy-preserving place. One of the other challenges that we have as far as all of these brand new techniques that we put together is, whilst we have people building these enterprise-ready open source libraries that can be used by individuals, enterprises, government, etc., a lot of the things that we do, they come from either research papers or experimental techniques that we're trying out. So we do build a lot of proof of concepts. We do actually try things out. Some of it we throw on the scrap heap because we realize this technique didn't actually work. We have a validation team that can validate algorithms. We, to make sure that our libraries are doing what they're going to do. But really, we do have this really great deliberate experimentation mindset. We do want people to go out and innovate. And so that's what you can get involved with as well. Is if you are someone who is really into trying some obscure new techniques, we've got so much for you to do here, and we've got the place and the support for you to be successful. If you think about OpenMind and our GitHub, is we do have 70 active repositories, or a little bit more than that. I know we have, I think, 71 when I last checked. We have repositories that turn on and off, but that's they're repositories that in the last month have had at least one commit. Most of them have had many more. We have over 150 monthly contributors to those repositories. That's always growing, and it has been. So whilst we have, I think there's like 500 plus contributors in the history of OpenMind, which is just over 3 years, we have about 150 per month now, which is pretty amazing. And our Slack community, we actually have 8,500, and I'm sure by the end of this convention it's probably going to be closer to 9,500. Maybe we'll hit the magical 10K, who knows. But we've got a very open, active Slack community with channels all over the place for all sorts of different interests, whether that's reading, ethics, privacy preserving, machine learning techniques, and whatever you're interested in, it's there. One thing I wanted to just touch on as well is, whilst I talked a little bit about some of the technical teams that you can get involved in, is we actually have these capability teams. And so we have, I guess, these techniques, approaches, all of these things that we're working towards fit nicely into one of these capabilities. Well, sometimes not so nicely, sometimes quite messily, and that is the fun of being in this open source community, is we can figure out how we can get these 6 key capabilities to play together. Each one of these capabilities, we have fantastic researchers, experts, we have industry folk. We really do have so much momentum in this space. And so if you want to come on board, doesn't matter whether you're a beginner or you're someone who's leading a startup that wants to implement what we do, is we've got a place for you. Please do. And the technical communities that I was talking about, again, this is part of I guess, we're being a virtual organization. We very much live on Slack. And so if you want to get involved, Patrick Cason leads our engineering team, and he helps cultivate and works with these technical communities. And so if you just come on board, join these channels, they're all like topic_something, and you will actually then be immediately thrown into a group of people who are working actively towards sharing skills and learning in these different spaces. And it is the place, when you're involved in these communities, where we'll actually find you, and if there's appropriate projects, we'll actually either advertise the projects, or we'll actively try to recruit you from these areas to join our core project teams. So there's so much more. This is a very, very tiny little taste of what you could achieve if you join OpenMined. And so just check out placements.openmind.org or join our Slack, and I'm sure that there's links everywhere to join our Slack, so just do it. And placement.openmind.org is where you can go and actually apply to be on one of our teams. Thank you so much, and I'll hopefully see you on Slack.
Thanks, Ben. Next, we're going to hear about the SIFT core team from Madhava J, who is joining us from Brisbane, Australia. Madhava?
Crikey. G'day. Hello from sunny Brisbane, Australia, and welcome to PryCon 2020. Now it's time for me to show you what I've been up to at OpenMined. Hi, and welcome to my talk on SIFT development at OpenMined. Who am I? My name's Madhava, and I'm from Brisbane, Australia. If you check my Slack profile, you'll see my current title is Human MyPy Linter. What is SIFT? SIFT is enabling the next generation of scientific discoveries by unlocking orders of magnitude of previously inaccessible data through the application of privacy-preserving machine learning. You can see on the right here a kind of example of what we're going for. Step 1, pip install SIFT. Step 2, execute your find cure algorithm. Step 3, collect your Nobel Prize in medicine. SIFT is a sort of Python bring your own code meta library that allows users to execute their existing deep learning or data science code for frameworks like PyTorch or NumPy on remote machines securely without ever seeing private data. What does that look like in practice? Well, instead of import torch, you can do torch equals alice_client.torch and get a kind of remote connection to torch running on Alice's machine. Every time you execute something, you will get a pointer which wraps around the return object. So you can see in the example here, we create a tensor, a two-dimensional tensor, and then we just transpose it with capital T. And inside the remote store, we can see both the original and the transposed tensor. Of course, in this example, we have a root client, which gives us the permission to call .get without actually requesting, but normally you would request permission. What are we working on at the moment? A reboot to SIFT, which is tagged as version 0.3. This provides support for Python deep learning and data science libraries, such as PyTorch, and it's going to expand to TensorFlow and NumPy very quickly. We're building the ability to automatically wrap and abstract arbitrary Python libraries into a sort of series of secure network pointers that can be used to invoke methods and functions remotely, all with privacy-preserving algorithms baked in. And underneath that, a deeper set of core libraries that will allow your existing Python code to execute across a kind of graph of nodes on the cloud and on premises, thus creating a global network of data and compute that we hope will drive the next big scientific breakthrough. Version 0.3 is a bit of a reboot. We're focusing on code quality. We have MyPy types on every single line. There's formatting and linting, code documentation, test coverage, a compatibility matrix for different versions of Python and its client libraries. You can see on the right here, my tests are passing 100%, so that's super cool. And of course, Duet, which is our two-player RPC data science kind of mode. To achieve this, we need to build a sort of universal Python wrapping system. Fortunately, Python provides us with a lot of dynamism and reflection tools, and so we're able to create this meta library, which can wrap nearly any other Python library with a secure RPC layer. As you may know, nearly all high-performance Python libraries have C and C++ under the hood, and this presents us with some unique challenges. On the right-hand side, you can see an example where we're dynamically generating classes using the Python type function. The goal is to allow anybody to come along and just use a PyTorch existing tutorial, such as MNIST, and they should be able to run that notebook on their machine, cell by cell, while having the code actually being executed on a remote machine with almost no changes to the code. What does the future of the development of SIFT look like? SIFT currently runs on a variety of platforms already, providing privacy-preserving machine learning on the cloud and on the edge on your mobile phones. We want to take this to every language and platform where private data needs protecting. But rather than maintaining dozens of code bases, we're looking to re-implement it in Rust. The core could then be a more thoroughly audited and tested code base, while we provide specific bindings that can give that first-class native end developer experience that people are looking for. Here's a sneak peek of what I've been working on. This is a Skunkworks project where I've taken a photo of my iPhone as it was executing the Rust core code bound in Swift inside the phone, communicating over the local area network on IP6 to a Jupyter notebook running Python, also running the same Rust core code, and it was just super fun to work on. OpenMind's always looking for talented and interested individuals to join our growing global remote first team. PRs are welcome and no contribution is too small. Remember, the journey to 1 million downloads begins with a single commit. Please join us on Slack and say hello. If you'd like more information on how to join, there are OpenMinders in your time zone who can help point you in the right direction. Thank you. Have a great PyCon 2020. And if you have any questions, don't hesitate to reach out to me. Bye.
Thanks, Madhava. Next up, we have Patrick Kaysen out of Sesimbra, Portugal, to tell us about the federated learning teams. Patrick?
Hi, my name is Patrick Kaysen, and I lead the federated learning team here at OpenMined. I wanted to go ahead and give everyone kind of an introduction to what the federated learning team is, what we're trying to do right now, as well as what we're going for in the future. So there's kind of two approaches that we take to federated learning. These are slightly different than some industry standard terms that you might have heard, like cross-silo or cross-device, or vertical federated learning, but they're quite similar. Model-centric is generally focused on edge devices, so where data may be deployed at a mobile phone or a web browser or something like that. While data-centric, on the other hand, is more close to a traditional data science workflow, whereby data scientists would inherently work with remote data. So we've actually built a bunch of libraries specifically for the purposes of model-centric. We've built SIFT.js for web browsers, Kotlin Sift for Android devices, and SwiftSift for iOS devices. All of these libraries have a lot in common. They can both perform both training and inference. The training data actually never leaves the device in the way that model-centric is organized. So training happens entirely on the device, and then a diff is basically sent back up to the cloud to be averaged. We have full support for Jewett authentication. We have network speed testing, and we also have support for either HTTP or WebSockets, depending on how you want to run your protocol. Mobile only specifically, we have support for battery charge detection, Wi-Fi and metered network detection, sleep and wake cycle detection, training in the foreground and in the background, and support for multi-threading on both iOS and Android. There's a lot more to be done at the moment that I'm doing this presentation. We are currently working on redoing our training API to support a variety of different future use cases, including the ability to do things like PubSub, as well as to have the workers drive the process specifically. So talking about the future, we're also going to add support for secure multi-party computation and secret aggregation protocols. That'll be done through WebRTC. And then we'll also add support for a JavaScript version of PyTorch, should one become available. Currently, there is no such thing. We actually have to translate any PyTorch commands using a library we also created called 3PO to TensorFlow.js. So at some point, we'd love to have more native support for the web. We'd love to add more commands to 3PO, our command translation library that makes all this possible. and then also allow for the ability to arbitrarily execute plans regardless of the cycle. So the way federated learning currently works is that you've actually got to have devices apply to a cycle. They're either accepted or denied, and the ones that are accepted basically have a certain amount of time to submit training back for aggregation at the end. It's our hope that we will also be able to support just arbitrary execution of plans whenever the device wants. And like I mentioned earlier, support for PubSub. Speaking a little bit to data-centric, so this is a little different in the sense that data will actually now be hosted in the cloud. That's the difference. In model-centric, you have your grid, which will be essentially hosting a model to train. And in data-centric, which is more close to cross-silo or vertical federated learning, you would actually have data being hosted in the cloud. So some data owner would run their own PyGrid node, and then data scientists can basically make requests against it. Our main core infrastructure is written in the node itself, which is kind of like your main central area. Data scientists would be able to provision environments on this node, and it would essentially create all the hardware specifications that they require, and then be able to train on those remote workers. If you add a network to the situation, this allows the data scientists to actually search multiple nodes simultaneously for a data set. So if you're in the process of discovery or exploring a bunch of different data sets and you don't have one in particular that you'd like to settle down with, then a network is a great way to explore data and see what's around you. So roughly how this would work is you start by searching for a data set that you'd like to work with. You can create a training plan or a set of operations to execute. You would send those instructions to a PyGrid node, and then basically a worker on that node would be created for you where the actual execution would be done. At this point, if the PyGrid owner decides to approve or deny the training of this model according to how it affects the privacy budget, so yes, we support differential privacy, and then lastly, they would release the trained model or inference result back to the data scientist. So going forward in the future, we'll want to add further support for differential privacy budgeting, the ability to both train and inference requests, deployment to all major cloud providers, starting with Amazon, Google, and Azure, and also support for serverless and server full deployment. There's one other thing, though, that I want to close on, and it's that we're building a user interface, and we could use a lot of really talented designers and JavaScript developers who are also available and interested to basically help us build a user interface that will manage both the model-centric and the data-centric processes together. So if you're looking to get started, you can send me a message on Slack, my handle as Serial Larceny with a C, or you can join us on our variety of Slack channels. You can also apply to join our team at placements.openmind.org. Thank you very much.
Thank you, Patrick. Moving on, now we'll hear about our cryptography team from Theo Raffel. Theo is joining us from Paris, France. Go ahead, Theo.
Hi, I'm Theo Raffel, and I'm leading the cryptography team. The cryptography team mission is to provide efficient, privacy-preserving algorithms for machine learning users to protect both data owners and model owners. Concretely, we design, implement, and integrate cryptography protocols that allow you to compute over encrypted data in order to perform encrypted inference or training machine learning models. Since the field of privacy-preserving machine learning is a very active area of research, our main challenge is to keep up to date with the most advanced and recent research in this domain, and to make sure that we provide the most efficient protocols to passive users. We currently have 4 main areas of research. We work on homomorphic encryption, secure multi-party computation, functional encryption, and private set intercession. Among our most exciting projects, we have wrapped the Microsoft C library to provide a tensor abstraction over an efficient homomorphic encryption protocol. This is a tensor library. We have also partnered with Facebook to integrate the Cryptin library to provide an efficient backend for secure multi-party computation in PySwift. We have developed several cryptography protocols, including function secret sharing, and worked with several researchers to continuously improve these protocols. As of now, we can already train and use in a fully encrypted way machine learning models. For example, we have released last week a tutorial to use ResNet 18 to perform secure inference over encrypted data. And we have many other nice demos that you can run on your laptop with basic knowledge of PyTorch. What are we currently working on? We're implementing new protocols from scratch, including BFV, that's a homomorphic encryption protocol, Falcon, that's an SMPC one, and many others. We are currently looking for Rust developers to help us improve the efficiency of some crypto protocols that are actually written in Python, and we are working for having CUDA support to have like great speedups. You can find our complete roadmap online in the OpenMined repo named Roadmap. Who are we? We are students, we are engineers, startups, researchers from around the world with different experiences and different backgrounds. Some of us are like discovering cryptography, some are more experienced in cryptography, but we work and learn together, so there's a seat for everyone. Why should you join? You should join if you want to play a role in bringing privacy-enhancing techniques to the greatest number, if you want every data scientist to be able to protect the personal data they use in a single line of code, or if you want to see people that don't trust each other starting to cooperate together in a positive way. If you're interested, please get in touch, check out our placement. Thank you.
Thank you, Teo. Next up, we'll hear from Alan Aboudib out of Montreal, France. Alan will be telling us about the natural language processing team. Go ahead, Alan.
So hello, everyone. My name is Alan Aboudib. I'm the NLP team lead at OpenMined. And I'm going to present and give you an overview of Ciphertext, which is the NLP library we are developing at the NLP team at OpenMined. And to be more precise, I will be talking about the new release we are going to make available in pre-con conference in a few days. So Ciphertext, let me begin. So what is Ciphertext actually? So Ciphertext is an open source library written in Python, and it leverages PySift, the flagship library developed by OpenMined, to provide capability for privacy-preserving natural language processing NLP. So I'm not developing this alone, of course. I'm developing this with a great team that whose members are just in front of you, and also some contributors coming from all around the world. So what's the problem actually? What we are trying to solve? So in this release, actually, we are providing the NLP, privacy-preserving NLP capability, but also we are providing the possibility to use PyGrid to host all the pipelines and the models you will be able to create. So there are, maybe we can distinguish 4 steps, and these are the 4, let's say, main capabilities you should be able to do with the new release. So the first thing you will be able to do is to create a local pipeline. It means when you work with NLP, you can define, for instance, tokenizer and some elements for pre-processing, which is like tagging words and excluding some words. And also, most importantly, you should also be able to create a deep learning model to do like a classification task, for instance, sentiment analysis, for instance. So in the privacy preserving settings, or when we have privacy constraints, say, once you create this pipeline locally using the library, the strings you are going to process are often situated on other workers, on other machines. Here, these are the strings. So Ciphertext should actually analyze this pipeline, and the parts that should do the pre-processing should be separated and sent to that remote worker, and training with the model, the last pipe component, should happen on your machine when you are trying to train your model. And actually, in a private, in a setting where strings are private, the data sets are private, you cannot see the data. So that's why Ciphertext also handles sending these pre-processing components to act alone and like remotely and blindly on that data and encrypt them and send it to you to be able, as a data scientist, to train on this data. And a very important capability is to be able to deploy this pipeline to PyGrid So here I show you just an example, and also to be able to use a deployed model. So ciphertext will also handle how once the model is deployed in the company and you want to use it, it will pull the pre-processing components to treat your string and like encrypt the embeddings, send it to the trained model, and securely getting the result back. So these are the main capabilities that we are working on. You will be able to see in the conference and in our demo in the conference. And if you want to help, actually, you can contribute in building ciphertext with us. So working on what I just explained and refining the process, and helping with future releases where we will support training these pipelines remotely, not only using them for inference when they deploy, also training them, and also coming up with use cases and paper implementations that we will, of course, welcome, and real use cases that might be good ideas to use in industry. So if you want to contribute, just go to the repo on GitHub, ciphertext, and read the README to see how things work and how you can contribute to us, or the lib_ciphertext on Slack to ask us questions, or placements.openmind.org to apply for our team. Thank you very much for listening, and see you in the conference.
Thanks, Alan. Next up is Will Abramson out of Edinburgh, Scotland, to tell us about the identity team. Will?
Welcome to the identity team introduction. Briefly, here's a few members of our team. Reach out to us on Slack or at the conference. We'd be happy to answer any of your questions. And I also want to emphasize, you are welcome. Like, if this interests you, give us a message, reach out. We'll find a way to fit you in for sure. So why is this stuff important? I mean, this has been important, ever since almost the creation of the digital space, really. And it's this iteration on, how do we interact online? How do we have assurance over the entities that we interact with? And, there's been different approaches to this. The current one that we're iterating on is this ability, this mental model that I should be able to have the same capabilities to interact with the service provider as they have to interact with me. We can interact as peers over this digital network. I do want to emphasize this point, this is touching human systems. It's not just a digital system. So it's really important, particularly as the lines blur between the physical and the virtual world, that we get this right. So this is, just a really brief introduction to self-sovereign identity. It's this idea that the issuer can sign credentials, pass them to the holder. The holder then can prove attributes were signed by this issuer to a verifier, without there being correlation between the credential and the presentation of that credential. It's based on, at least some versions are based on anonymous credential cryptography, which is really the maths and the cryptographic proofs that make sure this is all private. I definitely recommend you checking this out. I'll drop a link to this mural space and you can come in and see it. So how does this fit into OpenMined? So highly recommend reading this paper that kind of kickstarted all this work. Me, Adam, and a few others wrote this back in May, or it was a while ago now. And it's really just looking at, okay, how do we use this self-sovereign identity systems to create this distributed trust framework within privacy-preserving machine learning flows? But I also want to emphasize, these are just ideas. This is a set of tools. We want you to come up with, within your flows, where does it fit? Like, come help us figure that out. We're still in that sort of learning space, right? We don't have the solution. We have some tools and we want to see where they fit in. I think healthcare is, a great sort of use case, a great context where you need identification and authentication. You can't just have anyone doing privacy-preserving machine learning on sensitive healthcare data. So quickly, I'm trying to be fast. I keep going over the time. Key objectives, we want to create excellent developer resources. We want to get you up to speed with the latest digital identity systems, the tools, so you can start integrating them into your flows. I think we've done a great job with this, as you'll see later. We've got some tutorials created. Hopefully we can get you up to speed so you can use this stuff today. We also want to, I'm really interested in cross-pollinating the ideas from the identity community, the OpenMined community with the identity space. Right, OpenMind's got this massive following, a great community. It's awesome. I would love to see a bit more cross-pollination between some of the folks that I know in the identity space. Let's bring them in. Let's try and get some privacy preserving machine learning folks talking to the identity people. I think there's a lot of unexplored potential there. Securing authenticated privacy-driven machine learning flows is kind of the thing that got us into this in the first place. How do we integrate this stuff into something like SIFT so you get a really nice interface for just adding it in without really knowing what's going on under the hood is cool. And then finally, I want to emphasize this point, which is, for me, I just knocked this up today, but I think anyone designing digital systems needs to be championing the design of these systems that respect human dignity, encourage self-organization, and limit the capacity for top-down control. So that's a key objective I wanted to chuck in there. And I'll just say, these are just put together today and open for debate. I welcome that feedback. Definitely get in touch. So what have we done so far? I mean, really, this is our playground, the OpenMined PyIdentity repo. It can be your playground too. There's the tutorials in there. There's 2 really great ones that we've put together, and I think they should take you from I don't know anything to, hey, I can actually build something and push it out into the real world. And then we have like a couple of projects that we're incubating, which potentially we can show you at this conference. We're not sure. Let's see how it goes. Finally, a couple of some research questions. If you have some more research questions, I invite you to add them here. Like, these are just some that I thought of. This is an evolving space. We need to be aware of that. We need to be open to change and keep thinking, basically. Yeah, so I think that is all. Hopefully I've not gone over time. There's some tutorials. I definitely, if you're going to do one thing from this, go and take our tutorials. It shouldn't take long, an hour, 2 hours, and you'll have a good idea at least what we're talking about. And then, I really recommend for people interested in what the future of this stuff looks like, read this report. It's excellent. Yes, so let's call it there. I just want to emphasize, I'm going to share this link to this mural space. There's a few other bits and pieces in here that hopefully will come together nicer, but I'd encourage people to put their feedback in here. You can just double click, you add a post-it note, put some content, and then potentially down here, like, watch this space. I'd like to just run a little experiment down here. It's part of my research and something that I've been interested in for a while, so let's see how it goes. Thanks.
Thanks, Will. Also out of Edinburgh, Scotland, our next presenter is Adam Hall, who leads the InfoSec team. Go ahead, Adam.
Today I'm just going to give a quick introduction to our team and what it does. So, when privacy-preserving machine learning comes into the mainstream, the effects are going to be felt in every sector of the data industry. We are here to help the AI community brace for impact by exploring the areas around trust and governance systems relating to privacy-preserving machine learning. Specifically, we'll be following these 3 categories: defensive capabilities, offensive capabilities, and governance. First, we'll be looking at host-based security tools like tripwires and logging and effective access control, but also looking at some guidance around how to create sanitized systems. Next, we'll look at some network-based security tools which we can use to protect the networks which we run privacy-preserving infrastructure on, such as firewalls, intrusion detection prevention systems, honeypots, and security incident event management platforms. Finally, we'll look at privacy-preserving machine learning workflow security and establish the synergies between tools implementing privacy-preserving machine learning workflows. The categories we'll be looking at are cryptography, differential privacy, distribution of information resources, and verifiable objects. So the second of these pillars is offensive capabilities. This will be looking into possible attacks on privacy-preserving machine learning workflows with respect to the confidentiality, integrity, and availability of these information resources. This exploration and documentation will in turn inform active testing of OpenMind's infrastructure. We'll be specifically looking at the areas of OpenMind's infrastructure vulnerability assessment, on-site application auditing and verification, creation of OpenMind architectures for pen testing exercises, and the design of scenarios which we can use to test these. Privacy-preserving machine learning specific governance models are necessary to bridge the gap between what's possible and what's legislatively justifiable. Businesses need to know why privacy-preserving machine learning is important, why it's going to save them resources in information security management, and most importantly, how they can justify it to their auditor. We'll explore privacy-preserving machine learning and InfoSec governance from the following perspectives: incident response, design ethics, legislation concerning privacy-preserving machine learning like GDPR and HIPAA, risk management in privacy preserving machine learning, information security standards like ISO 27000 and NIST, and the synthesis of these in the context of privacy preserving machine learning. So if you're interested in any of these problems, then join the Slack and reach out. Cheers.
Thanks, Adam. Our final development team presentation will be from Patrick Hunter out of Richmond, Victoria, Australia, to tell us about the validation team. Take it away, Patrick.
Hello, I'm Patrick Hunter. I'm the validation team lead here at OpenMined. The validation team is a bit unique to OpenMined. We sit between security and quality control in the gap, or arguably overlap, between the two. OpenMined has an unusually large amount of projects that give specific formal guarantees around security and/or privacy. So the validation team's role is to check that those guarantees hold in practice. That's a bit abstract, so I think it's worth going over our current main project as an example. PyStatDP is a Python program for statistical counterexample generation for differential privacy. What that means in practice is that we take differentially private functions written in Python and try to generate example inputs that cause them to break their differentially private guarantees. And the way we do this is by algorithmically generating a huge number of examples and running each one a large number of times, then trying to reverse engineer the input from the output and seeing if we're able to do so to a greater extent than is allowed by the privacy guarantee of the function. And if we do generate a counterexample, then we can pass that on to the dev team for fixing. And if we don't, then we say that the function has passed validation. While there are some caveats that are a bit outside the scope of this talk, we have set the number and type of inputs that we generate to be large enough that if a function passes, it is statistically very likely to actually be differentially private. In the near term, we are looking at making some quality of life improvements to PyStatDP and then rolling it into the continuous integration pipeline for PyDP, which is our Python-based differential privacy project. In the slightly longer term, we are looking at expanding languages, expanding what sort of things we validate, such as privacy of private set intersection, and possibly rolling in some formal verification methods, though that's basically if any of you happen to already be really familiar with those and want to volunteer, we think it sounds cool, but it's not a priority. That does bring me on to the next point, which is we are heavily recruiting for more team members. Our requirements are pretty open. If you happen to have directly relevant experience in security or quality control, that's great, but we have room for both general programmers to help us with the implementation of stuff and general mathematical researchers who are willing to read through a bunch of academic papers like the one we used as the basis for PyStatDP and report back on ones that are worth integrating into our projects. If that sounds interesting to you, you can reach me on the OpenMined Slack. My username is Patrick Hunter, and I check it about once a day. Or you can also take a look at the PyStatDP GitHub repo. It's under OpenMined/PyStatDP, so pretty easy to find. Thank you, and have a nice conference.
Thanks so much, Patrick. And thank you to all of our team leads who presented today and to all of you guys watching. I hope this gives you a really good insight into all of the different ways you can fit into the world of privacy-preserving tech and into OpenMined. Once again, my name is Amber Trask, and I'm here to help if you need anything. Please feel free to message me on Slack or shoot me an email anytime. Next on the conference agenda is our networking hour, so head on over to our conference gather space at gather.openmind.org, and several of our team leads will be hanging out ready to answer any of your questions. Have a great PryCon 2020, and I'll chat with you soon. Thanks!
Hello, everyone. My name is Zachary Charles, and today I'm going to be talking about some exciting work that we've been doing here at Google on adaptive federated optimization. And this is joint work with a lot of great people at Google. Sashank, Manzel, Keith, Zach, Jakob, Sanjeev, and Brendan. I don't have too much time, so I'm going to get right to it. First, just an overview of what adaptive federated optimization is all about. And really, the goal of this work stream is to improve optimization methods for federated learning, FL. And at a high level view, what this is about is we want federated learning methods that automatically adapt the client and server training to heterogeneous user data. For those of you not familiar with federated learning, just remember that it involves the server broadcasting a model to clients, the client's doing some local training, that's A. B represents kind of all the different heterogeneous client models that are then sent to the server again, and that is used to update its own model. And so really what we're about here is the idea that different clients are going to have very, very different data in federated learning. And this makes optimization a challenge, especially because federated optimization is a really new area that I think I would go out on a limb and say that not too many people have real good intuition about. And so we tackle this problem to some extent, and our main contributions are as follows. We develop novel and practical methods for federated optimization. We benchmark these methods on a really wide variety of tasks and models, and we provide an open source implementation of all of this within TensorFlow Federated. And so just some things that are important here. Two of the difficulties in this work stream were hyperparameter tuning and kind of a lack of consistent benchmarks in the field, and I'll get to that. So research overview. Federated optimization is something that really occurs in two different levels. There's client optimization and server optimization. So this diagram kind of gives a very high-level view of what's going on. The server model here gets broadcast to the clients, and the clients do some local training. That involves the client optimization. Now, once the clients are done training, they send their model back to the server. The server takes all of the client updates, and it somehow updates its model. This is where the second level of optimization, the server optimization, comes in. In federated averaging, if you're familiar with that, it does a really simple update. All it does is average the client updates and use that as its new model. But you could imagine doing something more sophisticated where we try to use stochastic gradient descent using these client updates as a kind of estimate of a gradient. And so what happens is that just by restricting to federated averaging, you might be hurting yourself in heterogeneous settings. And this is particularly true in natural language processing, where a domain where users have very different vocabularies. So over on the right, I have a plot. This is a next word prediction task, and it's on a realistic heterogeneous data set. And we've plotted here what happens if we use SGD on the server versus SGD with momentum on the server. The clients just use SGD. And this is with tuned server learning rates and client learning rates. And what we see is that there's this huge gap between what happens with standard SGD and what happens with SGD with momentum. And this really begs the question, what else can we do? What if we start using even more sophisticated methods for optimization within our federated setup? And so we just devised a general framework for federated optimization that explicitly accounts for client-server optimization. And it recovers a lot of really popular methods such as federated averaging. We call this FedOpt, and you should really think of this as a collection of algorithms. And what's really important is that FedOpt incorporates a client optimizer. You get to pick what you want. That happens on the clients, obviously. And a server optimizer. That's the optimization happening at the server. And what's really important about this is that client optimization is fundamentally different from server optimization. In a lot of settings, clients only participate at most once because there's so many clients. Clients generally only perform a small number of steps, whereas the server is present throughout, and it can hold on to things in memory, so it can preserve state throughout the algorithm. And this makes the choice of client optimizer and server optimizer very different. What you're looking at is that the server optimizer might be better suited for very sophisticated algorithms. And this is exactly what we do. We incorporate adaptivity into the server. And the reason that we use adaptivity is that adaptive methods are really, really important in a lot of machine learning contexts. We've seen this explosion in the use of methods like ADAM and AdaGrad, and now there's all kinds of variants that have, pros and cons. But these are undoubtedly important to the empirical success of machine learning methods. And so what we do is we incorporate this adaptivity into our federated learning experiments in a way that is theoretically justified and empirically justified. And we provide easy-to-use open source implementations that really are about benchmarking and making reproducible our results. And so what I've shown here, this is the update for AdaGrad that involves this kind of preconditioner matrix that is learned according to the heterogeneity of your coordinates. This is a coordinate-wise update rule, and we incorporate this onto the server. So the results, accomplishments, we designed 3 new adaptive federated optimization algorithms. We call them FedAdaGrad, FedYogi, and FedAdam. And these are versions of our framework where the server uses an adaptive method such as AdaGrad, Yogi, or Adam. Yogi, for those of you not familiar, by the way, is a variant of Adam that involves kind of a more conservative approach to changing the learning rate, and has had a lot of great empirical success recently. And so we analyze the convergence of these algorithms, and we show that they are justified, and that they can recover essentially the same asymptotic convergence rates as mini-batch SGD. And the fact that the asymptotics are the same shouldn't be too surprising, in the sense that AdaGrad, for instance, has a similar asymptotic convergence rate to SGD in the centralized setting. But where things start to get improved is in kind of non-worst case scenarios when you actually are dealing with sparse data. And so we'll get to the empirics, but these methods generally perform much better than just SGD. So like I said, we implement these in an open source way on really 6 different tasks. And so this, we use 4 different data sets. We use CIFR100. We train a ResNet with group norm layers. We use this EMNIS data set, which is a digit recognition data set that is naturally heterogeneous, partitioned according to the writers of characters. We do digit recognition and autoencoder tasks on it. We use the Shakespeare dataset, in which each client corresponds to an acting role in a Shakespeare play, and the data are their lines. We do next character prediction. So character is in A, B, C, D, that kind of character. We also use the Stack Overflow dataset, which is a collection of posts on Stack Overflow. So the clients are users, and their data are their posts. And so we do 2 different tasks there. We train an RNN to do next word prediction. And we also use a logistic regression classifier on bag of words vectors to do tag prediction. And what's important is that this is actually now a convex task. So it's a good way to see behavior on different kind of loss functions. So let's get into what the actual empirical results are. Basically, what we found is that adaptive optimizers significantly improve upon non-adaptive ones in a lot of different tasks, and do at least as well on the non-adaptive optimizers in all tasks. And so I've plotted 4 of the results here. I think these are the 4 most important in the sense that I've omitted the EMNIS ones because EMNIS is kind of a simple data set and it's pretty easy for most optimizers to do well. So on Shakespeare, what we see is that FedAdaGrad, which is this federated version of AdaGrad, is actually much better initially than other methods, and eventually ends up being a little bit better than other methods such as federated averaging. CIFR100, we see a similar story where federated Yogi and FedAdam do really, really well. And they actually do a couple percentage points better than federated averaging with momentum on the server. That's what this FedAverage-M is. And much, much better than federated averaging. Note that we do see FedAdaGrad kind of fail here, and that's because this is a very non-convex task. It should be noted that image classification is something historically that SGD with momentum is really, really good at. So it's not surprising that FedAverage-M does really well here. However, once we get into language modeling, things become much different. So for instance, this is the Stack Overflow logistic regression task. This is the tag prediction. We've plotted the recall here. And we see an absolutely huge difference in what's going on with the non-adaptive methods, that is federated averaging, FedAverage-M, and the adaptive methods. And what's going on here is that some of the tags are so infrequent that when federated averaging, FedAverage with momentum see them, they don't make enough progress. And so this adaptivity is really, really important to make progress on clients who have rare tags. We see a similar thing on next word prediction. And again, it's these rare words that we're really seeing the benefit of adaptivity. And so we have a table here kind of showing the best result within a couple tenths of a percentage point for each task. And really what we found is that FedYogi did at least as well as all the other algorithms throughout. And so this code is available for comparisons externally. Yeah, so if you have a desire to use it, please do so. And please contact us with any questions. So some future work. This was adaptive server optimization that I talked about. And you might imagine that, well, what about adaptive client optimization? That might seem much more natural. This is a hard thing to incorporate, though. Clients usually only take a couple steps. And now, since they don't necessarily maintain state, especially if you imagine that they're smartphones that just participate once in a while, you're going to have to learn the preconditioner in a very federated manner in which you're going to have to do extra communication somehow to learn what this preconditioner is going to look like. And so it's an ongoing question of how exactly are we going to incorporate client adaptivity. And we think that we can combine it with compression and kind of an extra communication step for this preconditioner that will allow us to learn a better preconditioner matrix in a communication efficient way. I am running out of time, so I'm going to skip this next open area and just move on to the future work. I just want to highlight that adaptive federated optimization can be used in tandem with other areas of research, such as differential privacy, compression, personalization, or your research area here. And some open questions are, how do adaptive optimizers affect privacy and utility of differential privacy? How about fairness? Do they encourage fairness by allowing clients with unseen data or like very infrequent data to make a lot of progress? And also hyperparameter tuning is really important. I didn't get a chance to talk about it, but it can be hard in federated learning. And so really we're interested in ways of making this easier. So just in conclusion, adaptive optimization methods have shown great promise in both simulation and practice. These methods have potential to benefit many topics in FL. And we're really trying to bridge FL theory, simulation, and practice. And so if you're interested in any of this work, please contact me or attend the live Q&A session. Thank you.
everyone, I am Miguel and I am a product manager in Google's privacy team. And today I am excited to talk to you about our differentially private journey. That is the journey that we took that was several years long to produce the differentially private infrastructure that powers a lot of Google's infrastructure nowadays and a lot of use cases. I'll talk to you about some of these cases. This is the agenda that I have for today. I'll basically focus a lot on building the infrastructure, the journey that we embarked on, going from the very basic level pieces to higher level pieces, and also talking to you about some usability aspects that we found in the way. So just to start, I'll let you know that getting to the point where we could build products with differential privacy from the ground up was a long journey. And I think there are three critical pieces that are important in that journey. The first one is building strong foundations. The second one is building frameworks that are familiar to potential users. And the third one is helping users navigate the utility privacy frontier. One of the first questions that we asked ourselves about 3 years ago was, why do we need the infrastructure? Around that time, we started seeing that there was an increasing demand to produce private data. At the same time, differential privacy started to emerge as a very solid privacy guarantee by passing the test of time. Therefore, we started exploring the idea of offering some basic components for internal teams who might be willing to try to use differential privacy. This is how we ended up with the idea of building foundational infrastructure that are the building blocks libraries that power a lot of our internal offerings. Our DP infrastructure starts with the foundational libraries. We started to work in these libraries around 3 years ago. Our vision was to power differentially private use cases that could accelerate developer velocity. Many times, people are just trying to experiment with a new idea. In this ideation stage, differential privacy provides a very good way of getting an idea off the ground by knowing the overall statistical trends, and therefore it allows the developers to start guiding their path towards a product development. The foundational library that we use at Google is the same one that we published and open sourced last summer. For us, it has always been really important to provide transparency around our implementation. We hope that all of you have had the time to poke around with the library. As I said, this library was launched around a year ago. And a few months ago, we also launched a Java and Go version of it, alongside Privacy on Beam, an end-to-end privacy framework that allows developers to compute differential private statistics in an end-to-end manner. In crypto, people say don't roll your own crypto. And that is because there are many pitfalls along the way. We think that this is also good advice for differential privacy. Reusing a hardened implementation is probably a good idea. As you can probably imagine, Google's infrastructure is very complex. So adding differential privacy natively to that infrastructure seemed back in the days like a gargantuan task. We also didn't know if the demand was there for a general availability service for differential privacy. To tackle this uncertainty, we piloted a version of differential privacy for a SQL engine that back then wasn't as widely used at Google. You might think that this was a small task, but it wasn't. A lot of our first users were processing terabytes of data and using those streams of data to produce differentially private results. The second step that we took was to build SQL engines. You might be wondering why we started there. The answer probably has to do with a hunch and demand. SQL continues to be a high productivity data analysis tool over large data sets. Back in 2017, we sensed that there was an increasing need to provide a privacy-preserving way of manipulating data. SQL is quite extensive in its use and easy to ramp up, so it felt like the right choice. I'll now give you a high-level overview of one of such SQL systems. As you can imagine, SQL allows almost anything. Many implementations are Turing complete. So enforcing differential privacy while allowing non-experts in differential privacy to write SQL that they're familiar with was quite a challenge. In particular, queries over events per user ID and changes to cardinality present big challenges. If you're not familiar with differential privacy, suffice it to say that the basis of differential privacy is quantifying the effect that a single user can have on the output. So the heart of a differentially private SQL must have the same property. We split and separate SQL statements into transforms within the scope of a particular user and statements made across the results of those individual transforms across many users. What this means practically is fully SQL compliant transforms of an individual's data, including joins, custom functions, etc. Completely unconstrained SQL, so long as it only occurs within the space of what a user owns and a much more constrained set of cross-user transforms. These cross-user transforms are based on the foundational libraries mentioned earlier and include all the basic statistical functions like mean, median, percentile, etc., while forbidding certain kinds of joins. Finally, though proving differentially private correctness is an essential part of the privacy engineer's mission, model checking provides a baseline level of confidence to the development process. As part of the foundational libraries, we employ stochastic model checking as part of a set of regression testing. While not a sufficient guarantee for differential privacy by itself, it quickly catches violations, both obvious and subtle, and provides a more stable backdrop to traditional privacy verification work. This is an example of a differentially private query. User-centric design was a big component of it. First of all, we want to make sure that a user understands that they are performing a private operation by adding the anonymization keyword. Next, we give users the opportunity to tune some relevant privacy parameters, such as epsilon. The query itself contains the anonymization function, in this example, a count and an average. Configurable per record confidence intervals are also released as part of any aggregated result. You can check out the details of our SQL implementation in this paper that we published and was accepted at PETS. One of the first applications for this infrastructure was a use case driven by social science related topics. About 3 years ago, we wanted to measure the impact of Hurricane Maria in mobility patterns. We partnered with scientists and produced a mobility map that was used as a proxy to measure the impact on mobility in Puerto Rico. Most recently, some of our colleagues published insights into human mobility using the foundational infrastructure we've built. Some more recent examples of products at Google that were built with differential privacy include the mobility reports, and just as of a month ago, the search trends symptom dataset. Now, I will talk to you a little bit about the utility privacy frontier. How will differential privacy affect my data? That is perhaps one of the first questions and most common questions that we hear from users trying to produce a differentially private output. This question arises from the fact that when we explain to people what's differential privacy and we tell them that it relies on adding noise, people get somewhat scared about it. So that's why one of the ways that we help users to think about this utility privacy frontier is by plotting the theoretical information gain resulting from applying a specific epsilon. This allows us to make informed choices as part of a privacy review process, but it isn't intended to be a guaranteed statement about outcomes or privacy guarantees. What you're seeing here is information gain that an attacker gets after applying differential privacy. And what you see is that if an attacker has a prior probability of 0.5, guessing whether someone was or wasn't in the dataset after applying differential privacy, their guess only increases to 0.516 up to 0.762. This is one of the ways we help users think about the utility privacy frontier. First, by plotting the theoretical information gain resulting from applying a specific epsilon. This allows us to make informed choices as a part of the review process. We also try to help users produce private statistics that help them understand the consequences of their parameter choices. Our goal is to allow users to make informed decisions, and what you're seeing in this graph is the overlay of the raw distribution of the underlying data with the differentially private distribution of data. Our goal with these types of graphs is to help users tweak some contribution bounds to allow them to extract the more utility from their dataset while still preserving some meaningful levels of privacy. We help users produce statistics that help people understand the consequences of their parameter choices. Our goal is to allow users to make informed decisions. Finally, in terms of lessons learned, it really takes a lot of time to build the right DEP infrastructure. There are many layers and there are many unknowns that we found out that were super important. Building it in a way that can be used by different use cases really pays off. I show you examples about mobility that we've published, but there are also other use cases that are internal to Google that have been extremely powerful. Third, putting an emphasis on the user is super important. A lot of people don't know what differential privacy is, and they shouldn't. And therefore, our job is to make their job easier. This is a great way to get people to adopt differential privacy. And finally, explaining the privacy utility frontier is key to gather user support, because only if they understand what's happening to their data, they will be convinced that it's the right choice. With that, let's go to Q&A.
name is Chris. I'm leading a team at Google building a system called TensorFlow Federated, or simply TFF, and I'm here to tell you about it. TFF is a new development framework for what we call federated computations. These are computations on data that is born decentralized, for example, on mobile or IoT devices, and stays on device where it was born. Federated learning is one example, federated analytics is another, and there's more. We're very actively using TFF at Google as a common foundation both for federated learning research and production deployment. And we'd like to evolve it together with you, with the open source community, to support use cases outside of Google. Now, what is TFF? You can think of it as having three major parts. There's a layer of new programming abstractions for the federated computations, for defining them, and I'll talk about this in a minute. On top of these abstractions, we have implemented various federated learning algorithms that are available through Count APIs, such as TFF learning. And finally, there is an extensible runtime infrastructure for simulations and beyond, and I'll cover that one in the later part of the talk. Now, I mentioned that TFF is a common foundation for both research and production deployment. TFF is designed to let you write code just once and then deploy it anywhere you want. So you can run it in a simulation locally in a Jupyter notebook. You can run it on a Kubernetes cluster across multiple data silos, whether it's within a data center or across multiple data centers. And you can also deploy it across a fleet of mobile devices. And so you have all this flexibility once you write your code. And to make it possible to enable this, TFF defines a small internal programming language in which you express these computations. So any code you write in TFF is serialized into a platform-independent representation in that language to give you all those different points of flexibility, and I'll explain that in a minute. But first, let's demystify what those federated computations are. As I mentioned, those are computations on data you can collect. Very often for privacy reasons, there could be other reasons. Data that remains on devices that may wish to remain anonymous, and there could be very many of them. That has certain implications in the real world. Let's explore those, and let's explore them on the example to make it less abstract. And so imagine we have devices with temperature sensors, and let's imagine, for the sake of this exercise, these temperatures are sensitive data. Right, and now analyst on the server wants to know what fraction of the devices have temperatures above some threshold. Now, again, temperatures being sensitive information, we can't just go ahead and collect them. And so we have to push the computation to the devices, right? So first, we'll broadcast the threshold to some subset of those clients. And now that each client has the threshold and its own temperature reading, and they can compare them locally. So that's the local computation, right? That's a simple one. And output 0 if it's below the threshold, and 1 if it's above, right? So this is, you can think of this as a map step in the map radius, a computation that runs entirely on the clients. Now, finally, with all these ones and zeros, all that's left to do is actually average them out and deposit the results on the server, and there goes the ratio that we're looking for, right? And of course, if you have thousands or millions of clients, you may have to repeat this process many times. So in each round, that will involve a broadcast, a map, and aggregation. We would potentially be talking to a slightly different subset of those millions clients. By accumulating the results across many rounds, we can get a more robust estimate. So now getting back into the abstract. And so we have many rounds that can potentially involve different subsets of clients that, as I mentioned, may wish to be anonymous. They can disappear at any time. And we don't know if or whether ever they will be back, right? So we treat them all as pretty much interchangeable, essentially stateless, right? Because you cannot rely on that state. You never know whether you will get it back. And so here, all the operations in clients have to be done in collective, just like in MapReduce, right? There's really no place in this programming model, in this kind of a framing, for manipulating individual client identities engaging in deliberate point-to-point interactions with specific clients, treating them individually. They're all just members of a collective. So in this model, the clients, as you see, do all the work, but the server also has an important role in orchestrating this entire process, aggregating the results. And of course, if it runs across many rounds, then carrying state over from one round to another as the subset of the devices changes between the rounds. Now, getting to the nuts and bolts of this, we introduced, as I mentioned, programming language that supports this. It has a distributed type system in which a value can be federated, as we call it, or distributed, so it can exist in multiple places. Temperature readings were an example of that, a value that was conceptually a single input, but that input existed in multiple locations on the different clients. Programs in this language are also distributed. In fact, the best way to think about federated computations is as little distributed systems, and the language we provide is a language that allows you to compose simpler distributed systems into bigger distributed systems, right? And these computations can have inputs and outputs in different places. So as you saw, our example had one input on the clients and one input on the server side, and that's okay, because again, it's a distributed system. And finally, the communication here is an essential part, integral part of this programming model and the language, not just some systems concern that's hidden underneath. Now, here's how you can express our example in TFF in an actual APIs that we provide. You start by writing a Python function, declare all the inputs and outputs wherever they are, so client side or server side. Now, in the body of the function, you can call the federated operators. And so you can see the broadcast, the map step that runs in the clients, and the aggregation, just like in the example that you saw previously. And finally, the local processing can be expressed in TensorFlow in this case, although we've designed our system such that other options can also exist. Now, all this code you wrote is traced just once and serialized into the platform-independent format that I mentioned earlier. So the whole process is somewhat analogous to what you can recognize in graph mode in TensorFlow, right? When you use Python as a syntax to define the program logic, but the actual program logic isn't Python. It's serialized into a form different from Python that is platform independent. Now, just so you have an idea of what the data structure is that represents the federated computations, here's what it looks like. It's purely functional. There's some lambda calculus in it and whatnot. Most importantly, I'd like to stress here that this platform independent representation is designed to be extensible. So there can be other types of local processing that we can incorporate for different kinds of deployments. And those can be incorporated into this broader framework that includes the lambda calculus, federated operators, and various other compositional constructs, just like those that you saw on the previous slides. Now, as I mentioned before, we've implemented various federated algorithms using these abstractions, and we made them available via canned APIs in TFF. And you can see examples of these in tutorials on our website. I won't dig into those. Just to give you a very quick example here, if you have a Keras model, it's a one-liner call to create computation that does federated training. Now, again, these are deployable anywhere you want, but for the sake of simplicity, if you just want to run a little simulation, you can also treat them just like Python functions and write simulation loops just like the one shown here. By default, if you do that, everything runs in a local TFF runtime that's transparently created under the hood for you in the same process. Now, you do have other options if you would prefer to run a distributed simulation, maybe for something larger. Again, we provide some canned APIs that make it very easy for you to construct different kinds of runtimes. For example, there's a tutorial on our website that shows how you can run things on a Kubernetes cluster. And again, you don't even have to change your simulation at all. You just set up a new Kubernetes runtime, set it as a default, and run it as usual. It's very easy, just the same way you saw in the example before. Now, we provide canned runtimes for, or what we call executors for the several of the common scenarios. And so by default, you get one that runs locally and can be multi-threaded on CPU or GPU. You can also easily set it up to run remotely over the gRPC interface. So you can use our executor, or you can implement your own, set it up remotely and connect to it. And finally, as I said before, you can run things on a cluster, and you can set it up potentially as a multi-tiered system with several intermediate layers of aggregators for scalability. And all these different architectures are actually supported by the same very small set of components, all of which implement the same generic abstraction of an executor. So an executor is a basic unit of composition in TFF for constructing various kinds of architectures. Let me say just a few words about it. And it's basically a box. An executor is a box with data and some computations that run inside of it. It supports 5 basic operations. The first one is to push some value inside into the executor, some payload into the box. So here we're pushing number 10. In response, you get a reference, which you can think of as being analogous to a tensor pointer. These references have asynchronous future semantics. So the computation may be still running. In this case, it's just uploading a number, so it's simple. Functions are also values in TFF. So here we are pushing another value. This time it's a function that takes a number and adds 1 to it. And again, you can create one inside of an executor. You get back a reference. With the 2, you can create a function call now. Again, you get back a reference to a results. And as I mentioned, it has asynchronous future semantics, and so that the reference will be returned to you before that computation potentially even started. And you can use it right away. So you can, you could form a tuple out of that and something else. You can make selections. And with all these basic constructs I've shown you so far, basically you can orchestrate arbitrarily complex kinds of processing inside of an executor, with graphs of cascading function calls. And the tuples and selections are here basically just so I can slice and dice results and move them around. And anything that's of interest, you can compute to retrieve from the executor, request the payloads, and potentially keep computing. And that's it. TFF provides a whole library of executors that specialize in different aspects of execution, such as multi-threading, or communicating over gRPC to some other executor, caching, processing lambda expressions, and whatnot. And all the different runtime architectures, from single machine to multi-layer distributed, are actually constructed from these small number of building blocks and composed in different ways. And so it's very, very modular. And this is designed to be extensible. And so here is actually, I want to thank our friends from Cape Privacy who have contributed new components to the TFF runtime to integrate with TF Encrypted. We are extremely happy to see this, and I would encourage you all to read their blog post. Okay, this brings us to the end. I hope that you can also find TFF useful and potentially contribute as well. And here, our extensible runtime stack is where I'm particularly hopeful to see some good opportunities to integrate TFF with various parts of the OpenMined ecosystem. If you're interested in exploring this, please do reach out to us. We'd love to hear from you. And that's all I have today. Thanks very much.
Hi, everyone. Thank you so much for joining me. I'm Kristen Lauder from Microsoft Research, and I'm the research manager for the Cryptography and Privacy Research Group. Today, I'd like to talk to you about my team's work on private AI, machine learning on encrypted data. This is a project that we've been working on over the last 5 years, and which has led to the development and the release of Microsoft Seal. Microsoft Seal is an encryption library which can be used to help protect privacy in AI applications. So the title of my talk, Private AI, Machine Learning on Encrypted Data, is intended to address the following problem. So the privacy problem with AI is that artificial intelligence or machine learning algorithms use a lot of data to make useful predictions. So they input your data and then output some kind of recommendation or image classification or decision. And the privacy problem is that you have to share your data in order to get the prediction. And typical AI services today are hosted in the cloud, run by some kind of a smart agent, such as Cortana. So the privacy solution that I'm going to talk about here very briefly today is a new mathematical tool which allows you to protect the privacy and security of your data through encryption while still allowing you to operate on that data and make useful predictions. And the tool is called homomorphic encryption. So I like to explain homomorphic encryption by relying on Homer Simpson. So homomorphic encryption, as someone tweeted in one of my earlier talks. So the idea of Homer Simpson here is that he's a jeweler and you have some valuable gold and you're going to share it with this jeweler in order to get some jewelry made. But since you don't trust Homer Simpson, he's looking pretty untrustworthy there. You lock your gold into a box and you ask Homer to work on that gold using this glove box that you see pictured here. And the glove box is locked and you keep the key. And you get the, Homer Simpson works on the gold through the gloves and then returns the box to you when you're done, and you unlock the box in order to get your jewelry. So that's the idea of homomorphic encryption, which is that it allows you to outsource computation on your valuable, sensitive, private data while still keeping the key yourself, in a sense, keeping it in a locked box. So what enables this? This homomorphic encryption tool can also be described in terms of its properties. Homomorphic encryption basically allows you to interchange the order of computing and encryption, and you still get the same order. So the same outcome. So homomorphic encryption homomorphic is a mathematical term, and mathematicians love commutative diagrams. So I'm showing the property here with a commutative diagram. It basically means if you have some data A and B, you can go across the top arrow and you can compute on it and then encrypt it. Or you could go the other way around the diagram. You could encrypt it first and then compute on it. And the encryptions that you get should decrypt to the same value. This also means that if you want to outsource computation, what you can do is you can take your private data A and B, encrypt it, and then send it up to the cloud, and then let the cloud compute on it and send it back. And you just decrypt the answer to get the outcome of the computation. So homomorphic encryption was an open problem for several decades. In 2009, the first solution was proposed by Gentry, which was considered fairly impractical and unimplementable. And computer scientists worked very hard over the next couple of years to come up with solutions that would be more practical. And in 2011, there was a surprise breakthrough from researchers on my team at Microsoft Research proposing a homomorphic encryption scheme, which is now used worldwide in almost all of the homomorphic encryption libraries. So we also introduced at that time a different approach to encoding data, which made homomorphic encryption much more practical, leading to about 4 orders of magnitude speed up in the technology. And then zooming forward to 2016, a project in my team, CryptoNets, was published at ICML 2016 and showed that neural net predictions were actually possible on encrypted data. Since then, there's been a lot of follow-up work from many, many teams. So the high-level idea of homomorphic encryption, the solutions that have been proposed and implemented today, is based on lattice-based encryption. But it's basically a very simple idea going back to even the idea of a one-time pad, which is that the encryption actually takes a message and encrypts it by blinding it, by adding a secret inner product, using a random value and taking the inner product with a secret vector. So if you actually have the secret vector, then you can actually decrypt by subtracting the secret vector. And what you'll get is the message plus a little bit of noise that you added. So if you hadn't added any noise to the blinding process, then you could easily solve it using linear algebra. And the noise is there to make it hard to cancel the secret inner product if you don't have the secret. So that's the property of homomorphic encryption, and that's a kind of a high-level description of how it works today. So let me talk a little bit about Microsoft Seal. Microsoft Seal is a simple encrypted arithmetic library, which we released publicly in 2015, and it's been widely adopted and used by teams worldwide. There's been an open source release of Microsoft Seal in 2018, which means it can be used for commercial purposes as well. It's available for download at sealcrypto.org, so you can go out there and download it right now. We also worked very hard in the last 3 years on a standardization process for homomorphic encryption because it's a new encryption technology. So we have a worldwide community, homomorphicencryption.org, which has agreed on secure parameters for using homomorphic encryption in practice. And again, you can go out to homomorphicencryption.org and download the standard. So I'd like to kind of give you an idea of how the performance of homomorphic encryption has improved over time. As I said in the beginning, in 2009, it was estimated that the overhead from using this technology would be something like 13 orders of magnitude. So this is a log scale diagram of how the performance overhead has come down over time. So as I said, in about 2011, when we introduced new practical techniques for encoding data to use in homomorphic encryption, we brought the overhead down to about 10 to the 9. That still seems pretty unreasonable. So if you can do an operation in plaintext in 1 second, the idea that you would have to spend 10 to the 9 seconds to do that same operation on encrypted data probably seemed pretty unreasonable. And it's why a lot of people persist in thinking that homomorphic encryption is not practical today. But through a combination of many improvements from the community and from our team, we've brought that overhead down substantially so that today there's many practical tasks, including machine learning tasks, that can be done with about a 10 to the 4 overhead, meaning if something costs you 1 second to do an unencrypted data, that it would cost you about 10 to the 4 or somewhere from 1,000 to 10,000 times slower. However, if it's an operation that you're doing in microseconds, that means that it's actually making the operation possible in a matter of milliseconds. And we also see the possibility for increased speed through acceleration using specialized hardware. So for example, GPUs or FPGAs. And you'll hear a little bit more about that in the next talk. So I'd just like to assure you that current performance numbers show quite optimistic performance for homomorphic encryption. So if you look at the first line of this table, if you use a lattice of dimension around 4096, you can see in yellow over here that the amortized time for doing homomorphic multiplication of ciphertexts, is about 1/4 of a microsecond. So that should assure you that the performance time is not too prohibitive to use in practice. So returning to the motivation for this talk, private AI, I'd like to call out a couple of different privacy problems that can be really solved with homomorphic encryption. So outsourced private storage and compute is one of the main applications of homomorphic encryption, which means things like private AI prediction services are possible, or things like hosted private training or private set intersection services, and even secure collaborative computation. So there's many different industries that could use this type of application, including finance, healthcare, and manufacturing, to do things like fraud detection or private medical diagnosis or predictive maintenance and data analytics. So over the years, I've given similar talks many times, and I've showed a whole range of demos that our team has developed to demonstrate the value of the homomorphic encryption technology and the SEAL library in practice. Starting with going way back to 2014, showing that heart attack risk was possible on private data. CryptoNets showed neural net predictions of predicting handwritten digits from the MNIST data set. We showed genomic predictions, predicting the flowering time of a flower, given an encrypted version of its SNPs, something like 200,000 SNPs from the genome of a flower, and mortality risk prediction, which is something that uses intelligible models. More recently, we've even shown like Twitter sentiment analysis on encrypted tweets, and image classification on images of encrypted images of cats and dogs. So today I'd like to highlight the fact that homomorphic encryption is a very useful technology that has been released by Microsoft Research. The SEAL library is available. Actually, at Build in May 2020, we actually announced the availability of notebooks for private prediction built on Microsoft SEAL. So you can actually go out and access the tutorial and the documentation for the Azure ML, SEAL on Azure ML to do private prediction and try it out yourself. So in conclusion, I'd like to just point to the next interesting talk, which will be given by Sadegh Riazi on Project HAYAX, which is accelerating homomorphic encryption with hardware such as FPGAs. So thank you so much for your attention. I hope you'll go out to sealcrypto.org and download SEAL and start using it to assure privacy in your ML applications. Thank you so much.
Hi everyone, my name is Sadiq Riazi and thank you for watching this talk. I'm going to talk about homomorphic encryption and how we can accelerate computation on homomorphically encrypted data. Before jumping in, I want to provide a very quick background on what is homomorphic encryption. Like any other encryption scheme, given a key, we can encrypt our data and make it unintelligible so that we can transfer it over the internet or store it securely. And once we have that, we can use the same or a different secret key to decrypt it and have the data intelligible again. However, unlike other traditional encryption schemes, homomorphic encryption allows us to do direct computation on encrypted data without having access to the secret key. For example, here we can have a server to run a neural network on encrypted data and send the result back to the client, where the client can decrypt and have the data available. On the server side, we are performing a couple of different operations, such as addition, multiplication, key switching, relinearization, rotation. I'll talk about these operations later. There's a small technicality that before encrypting, we have to encode our data, which is the process of making it ready for encryption. And also after decryption, we have to decode the data to make it available. So what can we do with homomorphic encryption? In theory, we can do any kind of applications. For example, we can have secure search, where we encrypt our search query and send it to the server that is responding to our search, and we can have the encrypted results we can provide the encrypted results to the client. And not only our data is secure on the internet during transmission, it's also secure from the server itself who is providing the answer to us. And the server doesn't get to know our search query or the results while providing this to us. We can have other amazing applications. We can realize secure cloud computing, where companies can easily outsource their computation and storage to the cloud without relying on the cloud for their data confidentiality. We can have privacy-preserving medical diagnosis, where hospitals can encrypt their data and send it to any other AI company for diagnosis. We can have privacy-preserving face recognition, where we can identify whether a person is within a certain list or not without disclosing the images of different people. We can have the benefits of personal genomics without sacrificing the privacy of our genomic data. The major obstacle in realizing all of these applications is the enormous computational overhead that comes with homomorphic encryption. Here we have a very simple example comparing the plaintext execution of neural network on regular data to executing neural networks on encrypted data. We see that there are several orders of magnitude computational overhead for typical applications. One very effective solution to reduce this computational overhead is to benefit from other type of computing platforms. For example, if we run homomorphic encryption on modern general purpose CPUs, we will see several orders of magnitude overhead. However, one natural alternative is graphic processing units, or GPUs, where we have many small parallel cores, and if we can distribute the computation effectively on these cores, we can improve the performance of the overall computation. GPUs are used in several applications, including rendering and machine learning applications. However, we can make this computation more effective for machine learning applications if we customize the chip for this type of computation specifically. For example, we can heavily optimize matrix multiplication operations and accelerate any type of machine learning applications compared to GPUs. And this is the idea behind tensor processing units. There is another category of computing platforms called field programmable gate arrays, or FPGAs, which provide us with a way to reconfigure the resources on the chip and to implement any hardware architecture that we want. And this gives us a great degree of flexibility. On a typical FPGA chip, we have several types of resources. One is digital signal processing units, and the other one is logic blocks. The third category is input-output pins that are responsible to talk to the rest of the system. And we also have on-chip memory, which provide a very fast and low latency access to store and retrieve data. We also have several networking switches on the chip that are responsible to correctly connect different parts of the chip to each other. For example, we can have one part of the computation being computed on this logic blocks, and then we store the data. Later on, we retrieve the data and pass it to this DSP units. A typical design flow of FPGA is to start with describing the architecture that we are interested in a hardware description language. Once we have that, we need to map this architecture to a set of logic gates in order to realize this functionality. The next step is called place and route. We need to map this conceptual description to physical resources on the chip itself, which we need to configure the networking switches as well as logic blocks. And at the end, we have a description of what needs to change and what has to be set on the FPGA chip in order to realize the functionality that we're interested in, meaning the original architecture that we designed. And this is the main goal behind Project Higgs at Microsoft. We want to accelerate homomorphic encryption using FPGAs and custom chips. The way we do this is, at the lowest level, we have designed several efficient modular arithmetic cores that are responsible for the lowest level of the computation. Building on top of that, we have low-level modules such as number theoretic transform, which, benefiting from many of these cores, are responsible to realize a low-level function. And building on top of that, we have higher-level functions such as key switching that we discussed, one of the key operations that is happening on the server side. And these module benefits from several lower-level modules such as number theoretic transform and dyadic multiplications. On top of that, we have our entire system, including the FPGA board and the host CPU. So let's discuss each layer in more detail. At the highest level, we have the system view, where we have the FPGA chip sitting on FPGA board and is talking to the host CPU and as well as to the off-chip DRAM. On the CPU side, each request is created and is passed over PCI Express to the FPGA chip, where we have different modules responsible to answering this request. And then once the answer is ready, we send it back to the host CPU. At level 3, we have high-level modules for high-level functions. For example, this one is for key switching. And as you can see, we have different types of modules sitting in this module. We have a number theoretic transform module and the inverse version of it. And then we have dyadic multiplications. The details are not really important in this talk, but one key point is that each of these modules have many internal cores. For example, as you see in this picture, this entity module has 16 entity cores. Here at level 2, we are seeing the internal architecture of number theoretic transform. As you can see, we have instantiated some entity cores, and in order to utilize all of these cores at all times, we have some machinery around this to provide the right data at the right time. And at the lowest level, we have modular arithmetic cores, which take a couple of inputs to the computation for us and provide the result. And this is the lowest level of the computation that we are seeing. One important notion here is that if we look at the micro operations over time, we can see that many operations are happening simultaneously on the FPGA chip. And in order to fully occupy all of these resources on the chip at all times, we have to create something called a pipeline design, where once computation is happening on one side of the chip, we are providing the input to the next computation so that at all times we are benefiting from the computation resources on the chip. In order to realize this, we allocate the resources on the chip proportional to the computation throughput that we want. And as you can see, because most of the computations correspond to entity computations, most of the chip area is consumed by entity. Here we see some performance results. We have implemented Higgs architecture as a proof of concept on 2 FPGA chips, one Intel Arria 10 and one Stratix 10. And here is the breakdown of resource utilization on different types of resources on the chip. Comparing to data center GPUs for number theoretic transform, we see, depending on the homomorphic encryption parameters, we see between 36 to 81 times performance improvements. Compared to modern CPUs, for high-level operations such as key switching or multiplication, we see, depending on the homomorphic encryption parameters again, we see somewhere between 160 to 260 times performance improvement. To put this into perspective, if we compare executing homomorphic encryption operations on modern CPUs, and we assign that baseline to HB RISC 50 megahertz processor, which was developed in '91, now we are looking at 64-bit Intel Xeon 3.6 gigahertz processor. That's the type of improvement that we are seeing using this new architecture. We can take our FPGA design and by following some steps, we can make it available and fabricate a custom IC for homomorphic encryption. There we can have additional 2 to 3 times performance improvements while consuming significantly less power. Going forward, we are going to extend the architectural support for other homomorphic encryption parameters. Here we have implemented the CKKS scheme, which is suitable for approximate computations, specifically in machine learning applications. We are going to extend it for BFV scheme, which is suitable for exact integer operations. We are also going to provide an end-to-end integration with Microsoft C library to accelerate any application without hand-tuning it. And at the end, we are extending our FPGA design to ASICs for faster computation. In conclusion, homomorphic encryption is a very powerful tool to protect our data while being able to utilize it. The major obstacle in utilizing homomorphic encryption at large scale is the computational overhead. And the proposed architecture in this talk, which is called Higgs, can improve the number theoretic transform computation by 36 to 81 times compared to data center GPUs, and it can accelerate high-level homomorphic encryption operations by a factor of 160 to 260 times compared to modern CPUs. In conclusion, there are a lot of interesting applications that can be realized today by this type of performance improvements. Thank you for your attention.
Hello everyone, Welcome to the talk titled Superfast Differential Privacy by myself and Gautam Kamath at the University of Waterloo. I'm a recent graduate from the Department of Computer Science and Mathematics at the University of Waterloo, where I majored in computer science and combinatorics and optimization, and I'm extremely interested in differential privacy, especially in the context of machine learning. So this talk is primarily going to be about how to run fast differentially private machine learning algorithms on modern hardware. And before we really get into the nitty-gritty parts of the talk, I'm sort of going to deliver the punchline as quick as possible. So this talk is really about how there's a lot of competing frameworks that allow you to do individual or access individual gradients, which will show us the crux of the problem for doing DPSGD. And we show that JAX, which is a framework that was developed by some folks at Google, is actually much faster than competing frameworks, and we hope that this encourages people to sort of adopt JAX and use it in order to prototype differentially private machine learning code faster on the GPU, and hopefully it encourages people to also pick it up. So to begin with, we'll start with the definition of differential privacy. And for those of us who have seen this before, there should be a quick primer, but I'm just going to succinctly summarize what the definition is essentially saying. So it says that if we have some neighboring pair of points that are close to one another, x and y, then it's very likely that a randomized algorithm, which we want to show as differentially private, m of x, will output a value or will observe a value that's extremely close to the value that we observe for m of y, where x and y are the 2 points in question. And we also highlighted some of the uses of differential privacy at scale at companies like Apple and Google. So hopefully, if you're interested in sort of how to take differential privacy or differentially private machine learning and push it to production environments, these are great articles that talk about how exactly these companies did it and why it's useful. Now we talk about sort of the workhorse algorithm for both this talk and also in general for deep learning that we've seen so far. So in general, for most deep learning models, the optimizer of choice is a first-order method that's some variation of stochastic gradient descent. And the natural extension to the differentially private world is sort of differentially private stochastic gradient descent. And this is really just adding 2 more steps to the regular SGD algorithm. And the 2 steps are highlighted in red, where we just clip the gradient according to some pre-specified value, and we add some noise where the noise is carefully chosen based on what kind of privacy guarantee that we want to enforce. If you're more interested in in each of these steps in more detail, please refer to the blog post. That's the first link down below. And if you're interested in some of the theoretical guarantees or how this algorithm came about, there's quite a few papers that I've listed down below that are sort of the introductory material to this algorithm. Now we talk about what the core of the problem actually is. So PyTorch and TensorFlow initially had a lot of difficulty in accessing individual gradients, and this is primarily because when deep learning came about first, we wanted to process batches at a time. And there was no reason to extract individual gradients because you would aggregate the loss over your batch and then process the gradient for that loss. However, for differential privacy, if we remember from the algorithm, we wanted to clip each individual gradient, which is different than clipping the average of the gradients. And so we actually require access to the individual gradients. And so I've listed a screenshot down below from one of the core devs of PyTorch, which showed that there was no way to actually access individual gradients in PyTorch. And if you follow the issue that I've linked down below, it also says that it's extremely slow if you'd like to do this, if you're just using vanilla PyTorch. Similarly, there are issues with TensorFlow's runtime, although TensorFlow does have some functions that allow you to vectorize over the batch dimension. So now I've listed some attempts at fast individual gradients because this problem actually was attacked by a lot of papers in the past, and these are some of them that talk about how exactly we can access individual gradients in frameworks like PyTorch or TensorFlow. The commonality to all of these methods is that they all present a way to sort of backpropagate each individual gradient, and then you can post-process it in whichever way you want. And for us, we kind of just want to clip the gradients and then add some noise to it. And these present pretty big speedups over just running each individual example one by one, which one might imagine is extremely slow. Now we move on to JAX, which is a high-performance machine learning library that's built on top of Python. JAX just-in-time compiles your code, or JITs your code, along with uses its own accelerated linear algebra optimizer to optimize your code and give you a kernel that runs extremely fast. JAX's API also resembles NumPy to a large extent, which means that if you're familiar with the deep learning ecosystem in Python, then you're also familiar with JAX's API to a large extent already. In addition to this, JAX also allows you to prototype in pure Python rather than prototyping in a framework or another library. In addition to this, one of JAX's core functions is this function known as vmap, or vectorized map, which allows you to parallelize across your batch dimension, and this essentially allows you to get individual gradients. So if we remember from the previous slides, we required individual gradients and we wanted it to be fast, and JAX gives us both of these things. Now we move on to the state of JAX for differentially private machine learning. Unfortunately, there aren't too many papers in the differentially private machine learning world that actually use JAX. In fact, in a Google Scholar search, we only found 2 papers that actually use JAX in order to run their code. In addition to this, we also see that competing frameworks tend to take a much longer time than JAX to actually run. And this means that a lot of the complaints about differentially private machine learning, which revolve around how much time it takes to prototype the code, are not as good of reasons anymore because JAX presents an extremely good solution to this problem. So we hope that this allows for a wider adoption of JAX, especially in the context of differentially private machine learning and differentially private stochastic gradient descent. We now move on to the experimental results section of the paper, where we compare JAX against the competing frameworks that we've mentioned before in the 2 architectures, which are convolutional neural networks and feed-forward neural networks. In the full version of the paper, we also mention a variety of different architectures and more frameworks to compare against. The model specification for the convolutional neural network is the exact same one that's used in most of the DPSGD tutorials, and it's just a convolutional layer followed by a nonlinearity, followed by max pooling, then a repeat of the same 3, followed by flattening of the output tensor, and then 2 linear layers with a nonlinearity in the middle. And the feed-forward neural network is just the last part of the convolutional neural network. We should also mention that for this talk we only focus on classification. However, in the paper we also look at regression as an additional task that JAX outperforms the rest of the models on. The first plot to look at is the feed-forward neural network, and immediately we see that across all batch sizes, JAX is significantly faster in median runtime than the rest of the libraries. We notice that the median runtime is reported instead of the mean runtime, primarily because JAX's mean runtime is slightly higher as a result of JAX's first epoch taking longer than the rest of JAX's epochs, because in the first epoch, JAX's just-in-time compiler is warming up. We should also mention that median runtimes are not the only metric to look at, and there are other metrics like memory utilization and GPU efficiency, which we also look at in the paper. Now we move on to convolutional neural networks, where we notice that the difference between JAX and competing models is largely exaggerated. The main reason for this is because JAX's XLA compiler allows it to compile certain parts of JAX's code into highly optimized kernels that are extremely fast to run. At its fastest, we notice that JAX is about 5 times faster than the closest competitor, which is Opicus. We also notice these results extend to a variety of different tasks, not limited to convolutional neural networks and feed-forward neural networks, that you can find more information about on the paper. We should mention that we were not the first to discover this behavior, and we're sure that there are experts in the audience who are familiar with JAX's extremely fast runtime for differentially private stochastic gradient descent. However, our search on Google Scholar led us to believe that not too many people knew about this. We're also the first to propose a thorough benchmarking of JAX against a variety of other libraries to show that it is significantly faster on all architectures that we've looked at. We should also mention that we're not any of the core devs of JAX, but we're just people who use it and we're not affiliated with them in any way. In addition to this, the full paper should be available at thesalon.ml/JAX paper. However, if you have any concerns or comments, feel free to ping us on Twitter at bGauthamKamath or at PranavSubramani. I hope you had a great time at this talk, and hopefully you find JAX useful in research or production environments. Thank you.
Hi, my name is Jason Mancuso, and I'm a research engineer at Kate Privacy, where I've helped build and maintain TF Encrypted with the team there. I became involved with collaborative learning through OpenMined 3 years ago when I helped create an early prototype of PySift. This talk is something of a retrospective after 3 years of wrestling with the research and engineering behind this technology. So first, what do I mean collaborative learning? I mean multiple data owners coming together to train a model while preserving some healthy amount of mutual distrust. So this would include, for example, federated learning or encrypted learning, but not encrypted inference and not differentially private training on centralized data. So what does it actually take to perform collaborative learning? This is an important question to answer to start talking about security. Well, we have this image, which is a representation of Google's internal system for federated learning. Now, this is a very specific flavor of learning, cross-device federated learning, where you control everything that you need to on the device because Google builds and maintains the full stack from Android OS all the way up to the Gboard application. Now, the really important question, I think, is how do we extrapolate this success to new use cases? So then I have to ask, what does it take to perform collaborative learning outside of this? And really the main bottleneck here is that the data needs to be compatible. And it seems simple, but data measuring some phenomenon can be captured and stored in so many different ways. And it's very likely, because of this, that data collected separately will lead to incongruous or incompatible data sets. They can't be transformed into each other without dropping a large number of either instances or even entire features from the data sets. An example might be in the US, health insurance claims. Now, claims data is more informative about patient health in many cases than medical records, since it tracks things that happen outside of the hospital. However, each insurance company has a different way of processing these claims and capturing data about them. Those differences ultimately make their way into each organization's data model, and so the data models end up mutually inconsistent or incompatible. There's a whole field of healthcare IT around this called interoperability. So we can zoom out and say that in general we have this disparate representation problem. The problem is that non-standardized data will almost always present some set of incompatibilities. Now, in theory, this problem should be solvable through standards, but let's take another look. So in the case of, again, medicine, we have FHIR medical records. This is a standard for storing and transmitting medical record data between systems. Now, in each of these cases that I'm about to show, we have something of a paradox where the fact that there's a standardized representation for medical records and the fact that data is being captured and stored at all can potentially exacerbate pre-existing biases in the data generation process. The circumstances and the biases they introduce are completely orthogonal to what the standard is intending to measure, which is the patient's medical history. In essence, the existence of standards does not magically fix the problems associated with bias data. So there are still issues at play, and they're probably magnified by the fact that we have multiple different data sets that we need to investigate this in. So we can call this the heterogeneity principle. It's essentially that bias is introduced whenever there are different data processing systems will manifest differently in ways that aren't easily distinguishable from just underlying differences in the data sets. So what all this tells me is that this picture that I showed, which is kind of like cross-silo learning, it's almost a pedagogical myth. It doesn't really exist outside of controlled laboratory settings. I mean, looking at this, it's hard to see it working in the case of all the data that I just described. Of course, researchers have been interested in fixing these problems. They've known about them, especially heterogeneity. And one of the potential solutions is local adaptation, where instead of having this magical service outside that runs the trained model, each data owner receives a copy of it back and then fine-tunes it within their environment and deploys it themselves. I think this can definitely help in a lot of cases some of those problems. But I do think that, more importantly, both of these problems need to be considered together. And future research, I think, should consider that learning across disjoint data sets of different modalities and distributions should almost be a fundamental research problem for collaborative learning. It shouldn't be some add-on that we study later. I've listed some examples here from the meta-learning literature that I think might suggest what collaborative learning would look like if we treated these as first principles. So while we wait for the research to catch up, what does it take to pull off now? Well, the main thing is that we need a high bandwidth social collaboration to build these systems. We need to collaborate with domain experts who know the data the best. We also need to have end-to-end access to the data pipelines that we're trying to collaborate across, because it's likely that we'll have to modify them into something that's unified for this joint data set that we'll use. And lastly, some kind of local adaptation is probably pretty essential. So why is pragmatic security hard outside of these data considerations? Well, if you're a subject matter expert, you'll recognize this somewhat as kind of the working taxonomy that we use when thinking about how these technologies relate under various threat models from the literature. Now, we may even have some idea of the relative complexity of engineering any of these for a given use case, but that basically means that this is all kind of wrapped up in this research world where it's mostly a dark art to be able to sort through these and apply them in certain situations. But I would point out two specific things that make this harder for practitioners. So one is that our tools don't reflect the true nature of these computations that collaborative learning runs. And the true nature is that they're heavily layered, and these layers can differ based on the use case. So for example, if you're looking at these right now, you have to build all of this from scratch for your use case, or go with a research framework, which is probably opinionated in all the wrong ways for what you're trying to do. Some of these levels should be chosen separately, while others should be chosen together based on the requirements. For example, you may choose a particular protocol because you have a particular learning algorithm in mind. For example, convolutional neural networks might be better suited for MPC in strong threat models. However, once you've chosen that protocol, you look at your convolutional network and say, well, actually, I could probably restructure this a bit to make it more efficient under this MPC protocol. And so you do that. So there's this kind of complicated interplay between each of the levels of these computations. And it becomes pretty clear once we think about it this way that what we need is a compiler toolchain that can take care of this stuff. But unfortunately, we don't have that in our tools, right? Instead, we kind of have to rely on our intuitions and our sparse experimental data about how these things combine. So there's a big gap in tooling and engineering here between what we would expect given the research. And so being pragmatic as a practitioner is extremely difficult without that. And now the second thing I would say is that while in research security is pretty well defined, in reality it's actually a spectrum, at least in this context. So in the context of collaborative learning, security is really a set of trust relationships built from the preferences of the participants. And these preferences are non-binary. For example, they can be a risk appetite for a given organization, which is going to differ based on the organization situation. And so security notions used in the literature are generally a poor reflection of this. Well, I've listed 4 examples here that I think could be in some ways more suited to the kinds of requirements that we see in common use cases in industry. I think they're pretty valuable. So I think ultimately what I want to get across here is that collaborative learning is stuck in a rut. I think it's largely kind of conformed to the bad habits of machine learning. It feels a lot like machine learning did before TensorFlow was released. But I think these are natural bottlenecks for a field this nascent to have. But hopefully I've been able to give some concrete recommendations about future research in collaborative learning, at least from an engineer's perspective. Thank you very much, and I hope you enjoy the rest of the conference.
Hi, I'm Samir. and I'm excited to present our recent work, Falcon, which is an efficient framework for privacy-preserving machine learning. This is joint work with Shruti, Fabrice, Eyal, Pratik, and Tal, and is going to appear in Privacy Enhancing Technology Symposium 2021. Machine learning has really transformed our society. We just see so many applications which at some level rely on machine learning to improve their services. Central to all these services is user data, and this has led to massive amounts of user data collection. On the bright side, it has also led to technological advances which use such data to improve these services. The question is, how do we actually enable such technological advances while also being conscious of the user privacy in this case? So here is a simple abstraction of what a present-day machine learning system would look like. On the left, we have a number of users who have data, and they share their data with this one centralized entity. And the centralized entity then uses this data to train a machine learning algorithm and provide a machine learning service. The issue with such a system is that the service comes at the cost of privacy. In other words, if the users are not willing to share their data, we can't enable such a system to work. So that's where the study of privacy-preserving machine learning systems comes into play, that how can we enable this service while also being conscious of the user's privacy? While there are a number of ways to bootstrap user privacy, for instance, using multi-party computation, homomorphic encryption, federated learning, I'm going to focus on multi-party computation for this talk and take it from there. Before we proceed, I'm going to quickly talk about some of the key takeaways of Falcon. So first, Falcon tries to achieve security against malicious corruptions. In other words, even if 1 out of the 3 parties is maliciously corrupt, we still want to have correctness of the protocol execution. Second is the evaluation over large networks and data sets. In Falcon, we try to scale up the evaluation to look at what happens when we run MPC over larger networks, and that's a second key takeaway. And finally, Falcon is highly efficient and is easy to implement. In other words, it's very, very performant compared to other works, as well as relies on simple modular arithmetic, which makes it very, very easy to implement. Let's take a quick machine learning perspective on the same problem. So this is what a simple machine learning network would look like. And like we do in plain text, we just decompose this network into its base functionalities. So on the left, we have the linear layers such as convolution, matrix multiplication. Then we have some activation functions, which are nonlinear functions typically, and then we could have division batch normalization. The key takeaway of MPC is that these nonlinear function computations, computing them exactly is expensive in MPC. And that's where a bulk of this work is also focused in. How do we actually achieve exact computations of these nonlinear functions, but in an efficient manner? So Falcon builds on SecureNN, and this is the functional dependence of SecureNN. If we look here, SecureNN relies on these 3 subroutines to actually implement a protocol for the derivative of ReLU. ReLU is a comparison function and is really essential to this entire privacy-preserving framework. And any improvement in the ReLU functionality actually amplifies because it's used many, many times over. So first contribution of Falcon is really to eliminate these 2 expensive subroutines into one subroutine, which immediately gives us 2x speed. So Falcon reduces, improves the comparison. Is to enable such is an important component of training large networks. This is just an example. secret with the other party, and now both of them have access to the reconstructed value. The moment we have a maliciously corrupt party, this party will arbitrarily deviate from the protocol and lie about their share. In particular, they can corrupt the output of this protocol, where the reconstructed value A need not be the true value which was to be reconstructed. To do this, under replicated secret sharing. So each party simply requests the share it's missing from one of the other parties, and now each party has the secret A. However, the system has redundancy and which can be used to enforce correct behavior, and in particular, each party can request the missing share from both the other parties. And since it's honest majority corruption, at least one of the neighbors of each party is honest, and hence we can actually compare the two values we receive from the other parties, and if they're not the same, we know that at least one party is behaving maliciously. So that's the basis, and that's the foundation of building the protocols in Falcon, and then we actually build these protocols to achieve the functionality while getting the privacy or the correctness from this paradigm. So I'm going to shift gears and move into some of the evaluation part of Falcon. So Falcon is developed entirely in C++ and will be released hopefully soon at this link. There's a lot of people who have been requesting me to release the code. So I'll try to do that as soon as possible. I again want to stress on the fact that protocols, once we build the base computation model of Falcon, like protocols are really, really easy to implement, and they can almost be read from the pseudocode in the paper to direct implementations. Finally, we also study a number of different networks, going from smaller networks, this is the number of parameters in these networks, to very, very large networks. So the first sort of quick result, I won't go into the depth of these, is really comparing the performance in private inference or private training of Falcon with prior works. Falcon generally favors very, very favorably compared to all these prior works. It's also very communication efficient, using a smaller ring size compared to prior works. So I won't go into the details of this, but I'll refer you to the paper where we also have results on the larger networks and much more comprehensive evaluation of these. One other interesting experiment which we did was we take the end-to-end time for private inference on these different networks and normalize them to 100%, but we split each one into two different components, the cost which comes from the communication and the cost which comes from the computation. As you can see here, as we go to larger networks, computation starts becoming a dominant cost in the entire network because the matrix multiplications happening in these networks have just become too large. This is a really interesting insight because it challenges our conventional understanding of MPC being communication bound. It's important to improve the communication complexity of the protocols, but once we go to large networks, it's also important to factor into the computation cost of these protocols. Finally, here's a simple experiment we run which really shows this thing. So on the left, we have the clear text computation happening over 64-bit floating point values. And on the right, we have the Falcon multi-party computation output, which is happening over 32-bit data types with all kinds of approximations in it. This is the output of running one batch. And so you have, on the left, we have one hot encoding, and then we have a batch size of it here, and then the same. And as you can see, the values on the left and right, and this is the beauty of neural networks, where the computation is so robust that even though the error accumulates, we can see a very small difference at the final values. We also run more experiments or more details on this experiment, and I refer to the paper. We have what's the relative error at the final network of the output of the final layer, and for that I refer you to the paper. With that, I would like to thank you for your attention, and I'm happy to take questions.
My name is Mayank Varia, and I research cryptography at Boston University. In this talk, I want to discuss some of the work that my colleagues and I at BU have been doing to make a cryptographic technology called Secure Multi-Party Computation, or MPC for short, more accessible and scalable for data analysts to use. But I want to start by describing why we think this is such an important problem to solve. So I want to tell you the story that begins in 2013, when the former mayor of Boston, Mayor Tom Menino, pledged to make Boston the premier city for working women. To identify ways to close the gender wage gap, he established a women's workforce council comprising industry leaders and businesses large and small across all sectors of Boston's economy, along with social advocates in politics and academia. This council established a pledge, or 100% talent compact. It has since been signed by several hundred companies in the Boston area. Compact signatories pledge to do three things: understand the root cause of the wage gap, use evidence-based methods to close the wage gap, and measure their progress over time. In this talk, I want to focus on that final goal, which I've listed on the bottom left of the slide. So the objective here is to actually measure the gender wage gap from real data, and they were able to get data from approximately 1/6 of the greater Boston workforce. I show on this slide examples of published reports that are available on the City of Boston's websites from their 2016 and 2017 data analyses. This kind of analysis was only possible because we've been able to use cryptography to protect the salary data in transit, at rest, and even while computing using MPC. The workflow for a company that participates in the wage gap analysis is pretty simple. They go to this website, 100talent.org, where they see a few tables that look like the following. This table requests basic demographic information about the number of employees at the company, broken up by gender, race, and job category. This table follows the same format as an Equal Employment Opportunity Commission form that many large employers fill out annually, so they already have this information at this disposal. Subsequent tables on this form look almost the same, except rather than asking for number of employees, they ask for salary information like the total salary and performance-based pay, again broken up by gender, race, and job category. With this information, we can not only measure the overall wage gap, but also better understand its root causes. So this is the information that each organization contributes. So what happens after they click Submit? Unlike most web forms, in this case, when an organization clicks on the Submit button, their salary data doesn't actually go anywhere, at least not in an intelligible fashion. Instead, what happens is that there's local client-side JavaScript that cryptographically splits their data into two pieces, one of which goes to a server that we run at Boston University, and the other piece of which goes to the Boston Women's Workforce Council. These two pieces are individually unintelligible gobbledygook. You can't make any sense of the information received. But the magic of MPC is that collaboratively, Boston University and the City of Boston can work together to calculate statistics or metrics of interest to the city. In this case, just calculating the overall city wage gap. MPC has been used in many other contexts as well, both in the private sector and is increasingly being looked at in the public sector. For instance, on the right side of the slide, I show a paragraph from a pending piece of legislation in the US Congress that, if passed, would use secure multi-party computation to collect metrics about the educational sector. The design of our 100talent.org website is unique in that it uses secure multi-party computation in the first place, and also because it's been strongly motivated by the design considerations for a variety of different stakeholders involved in this data analysis pipeline. I'll describe 4 of them here. First, there are the actual HR personnel who are the ones tasked with uploading their organization's information into this system, into this interface. For them, our primary concern was ease of use. That's a big reason why we're using a web browser interface rather than asking them to install any software or do anything that could be a barrier to using the system. We also ran many different training seminars, both in person and online, to make sure that they were familiar with the system and how it worked. The second stakeholder was the Boston Women's Workforce Council. Their primary concern was the accuracy of the results, given that, due to the nature of MPC, They can't look at the data to do any kind of manual post-processing or filtering of erroneous results. For this reason, our website has a lot of client-side JavaScript that runs on the organization's side to identify proactively if it looks like they're making a mistake with data entry. Our third stakeholder are the IT personnel at the organizations that are contributing their data into this analysis. For them, a big concern was to make sure that they understood that the system is actually doing what we claimed it is doing, that it is easy for them to audit and verify that the website is behaving properly. And for that reason, all of our code is open source. Our initial system was a very bare bones system that had just a couple hundred lines of code, although it's since grown a little bit over time to add more features. You're welcome to visit github.com/multiparty to see the code for this project and the others that I'll describe later in this talk. Finally, lawyers at the data contributing companies were worried about risk and the liability if something should go wrong. Some of them asked us to sign non-disclosure agreements stating that we would not hand out their salary information to anybody else. This is a document that we were able to get the BU Office of General Counsel to sign because, due to the nature of MPC, we weren't ever receiving their salary information in the first place. So that's our system for making MPC easy to use on the web. In my remaining time, I want to pivot and talk about a different system that we've built to make MPC scalable so that you can do analytics over very large data sets that are held by different private organizations that want to do some collaborative data analysis, but they don't want to share the data with each other. This system is called Conclave, and it works as follows. You can have an analytic that is specified as an ordinary SQL query. So the analyst does not have to know anything special about MPC. And Conclave will split this SQL query into components that are executed using MPC on different providers' existing data parallel frameworks like Hadoop or Spark. You don't have to put your data in a different data engine or platform in order to use it with Conclave. Conclave also includes static analysis tools that will opportunistically identify places to improve performance without compromising on privacy. Specifically, it will rewrite the query in such a way that it tries to front load as many operators as possible that can be executed locally on each individual backend without the need for MPC so that it minimizes the amount of work that needs to be done globally by all parties. This helps to make MPC scalable to larger data sets. Finally, we include a dispatcher that makes Conclave easier to use either in a peer-to-peer setting between different private organizations or on a multi-provider public cloud. Because Conclave has many moving pieces, like the data parallel stacks that do computation in the clear, and the MPC engines built by us and other people that do the global part to do the global aggregation, there's a lot of different software components. So our dispatcher allows for push-button operation, where once the analytic is specified, it will create containers and execute all the various components of the system on the different backends for you. Finally, one ongoing project of ours is to use FPGAs to have hardware-accelerated MPC in the data center. We think that FPGAs are a great fit for MPC because FPGAs offer the ability to parallelize a lot of computation, and MPC tends to be embarrassingly parallel. And also, FPGAs in the data center offer very fast network connectivity speeds, very high-speed interconnects, which comes in very handy because MPC tends to be communication-bound in practice. Our initial experiments show that we can design an MPC system on an FPGA that allows for both arithmetic and Boolean circuits, and the punchline is you can basically get the equivalent of a 200 megahertz CPU processor. So that's slower than ordinary processors, but you get the equivalent of a 200 megahertz processor with the huge benefit that all of the computation is being done in a cryptographically protected fashion, and none of the individual participants in the system know what the data say. In conclusion, we believe that making MPC more accessible and scalable can fundamentally change the way that we go about data analysis. Rather than having to think first about what data you can acquire and then trying to think about what questions you can ask of that data, you can flip that around and first decide what question you want to answer if you had access to all the world's data, and then figure out how to protect that access sufficiently so that the data owners consent to participate. Thank you for your time.
Hello, everyone. My name is Luca, and I'm the research lead for the Machine Learning Ethics, Transparency, and Accountability team here at Twitter. Today, I'm going to talk to you about the data set that we released for the Rexis Challenge, and specifically the privacy consideration that went into design of this data set. However, before we start, I would like to mention that it really takes a village, and I would like to thank all the people you see on the screen that have worked hard and helped us for this. So we'll start with the motivation why we have done this in the first place. I will spend some time describing the data set, and then we'll focus on what privacy consideration we thought in the process. So the first obvious question is why? Why have we decided to organize this challenge? Well, as you know, recommender systems are a very important part of social network, and if you think about that, Twitter can be thought as a giant recommender system. The Twitter timeline, which is the main thing you think when you think about Twitter, is a giant recommender system where we are trying to recommend to you the tweets that are most relevant for you at that given time. Therefore, finding the best recommendation system for us is really vital. Second, we believe that large-scale standard benchmarks can really help advance the field. For example, computer vision really benefit from the release of this massive dataset, ImageNet. You could even argue that computer vision will not be here where it is now if not for this dataset. And so we believe that Twitter has an interesting set of challenges for the research community, and we'd like to provide this data set in the hope to accelerate research in that direction, in this area. So let's talk a little bit about the data set. The data set, each row of the data set consists of one of 4 engagement types. So, we have an author that created a tweet and a reader that potentially saw this tweet and either engage or not. And there are 4 types of engagements, like, reply, retweet, and quote. And, we have a bunch of features, some for the users, both author and reader, some for the tweet, and some for the engagement. And we collected 200 million samples over a 2-week time frame. We sample for training 160 million the first week, and then 40 million over a subsequent week divided in validation and testing. To our knowledge, this makes the data set the biggest social network data set so far. Now, before doing that, we had a lot of thoughts on how we could best preserve the privacy while at the same time creating a data set that was useful for the research community. And I would like to share with you today some of the consideration we had. So the first thing that is important to understand in intervention is that everything we release was already public. You connect to the API today and get the exact same data. As a matter of fact, you will get more data if you connect to the API than what you released. At the same time, I would like to acknowledge the fact that the API is not free. Even though this data set is technically public, it might not be available for everyone. The other thing we did was to obfuscate IDs of users, tweets, and everything else. We are very aware that this is not efficient technique at all, especially when the data set is already public and available somewhere else. We did wanted to still do this step in order to prevent sort of like zero effort misuse of the data sets. In the same fashion, we wanted to have, we wanted people to be able to use sort of all the information and the richness from NLP models, but we didn't want to provide the text as it is, right? Because then you could just copy and paste the text in, your favorite search bar and find the exact tweet. Therefore, what we have done was to replace the text of the tweet with the BERT tokens of the tweet itself. In that way, we thought we had a good compromise between, making sure that people could use pre-trained model, but also sort of like preserving or not making the tweets immediately available for everyone. So an interesting thing is how we create the negative in the data set. So, when you're creating a data set, you need like some positive example and some negative example. Positive example are easier. It just means a user engaged with a tweet. All the engagement type we've considered in this challenge and for this data set are already public. So we know it's public available if someone interacts, likes, replies, retweets some tweet. However, a negative sample, an early example here would mean someone who saw a tweet, yet decided not to engage with that. The information of someone seeing a tweet without engaging is not a public information. Therefore, we try to go around this limitation in the following way. Instead of considering the tweets that were seen but not engaged with, we considered all the potential candidates for this. So we created, for each user, for each reader, we consider all the tweets that were created by the people they follow. We removed the tweets that this person interacted with because these are positive examples. And now we are left with this pool of tweets that the person definitely did not interact with, but we don't know if they interacted because they never seen the tweet or they interacted because they did not like the tweet, yet seen it. And so we just sample from this data set. So to reiterate, the data set has a bunch of tweets, the negative example, of the data set have a bunch of tweets that were not interacted with, but we don't know for a fact if the person saw them or not. And finally, this is a very important point, the data set is kept in sync with Twitter. So if a user deletes their profile, deletes their tweets, or puts their profile as private, everything will be reflected in the data set. I just want to mention like a couple of limitations of this data set. So the first one related to my last point is this data set is actually shrinking because we had like this fixed week that we sampled from, or 2 weeks. And then people keep deleting. It can only go in one direction. You cannot add a tweet for the past. Therefore, our data set over time is shrinking. But I want to mention the data set, it's still there and it's still available for research. So please go and use it. Also, the rate of shrinking, it's slowing down because people are more likely, or I should say less likely, to delete tweets from the past. Another thing, in production, there are other things we're interested in, not just accuracy. Latency is a big one. You want everything to be fast, and in this year, the challenge latency was not captured. There are more details on the paper we wrote, so please go and check it out. And I'm happy to get any questions on Twitter, I guess. Thank you.
Hello, everyone. My name is Patrick, and I'm here with my colleague Adrien. We are representing National Bank of Canada, one of the biggest financial institutions in Canada. And we're here to present our work on generating synthetic transactional profiles. Let's start by giving you a little bit of context. In the last couple of years, Canadian institutions had major data breaches. For example, Equifax in 2017, Desjardins in 2019, and very recently, the CRA. This made people realize that insider threats, among other causes, but this one being one of the causes, is very real and have huge consequences. Giving access to sensitive data to an employee is always a risk. But of course, you also want to bring value to customers with data. So that's the challenge we face as big institutions. Many teams are working on these questions at NBC, following industry standards, of course, but with my colleague Adrien, we wanted to think a little bit outside the box, and we asked ourselves, what if we could simply get rid of clients' data in our data science projects? That sounds a little bit crazy, but that's how we ended up with this approach, which is generating synthetic data. As a first use case, we chose transactional data. So this is how it goes. In the middle, you have a model that replicates the distribution of the transactional data of NBC without revealing any personal information from any of our clients. The way you train the model is you feed it inputs. So the transactions on the left, you can see, and you can also add maybe other information such as socio-demographic data. The model learns to generate very similar transactions, and that's the output you see on the right. Once the model is trained, you can remove the inputs, and you can use the generative model to sample transactional data. You could also decide to keep the socio-demographic data as input to have a conditional generative model. So why did we choose transactional data? For three reasons mainly. First, although they are not considered as PIIs, they are very personal due to their high inference power. Just with a couple of transactions, you can almost certainly identify a client. Second, they're very strategic for the bank. We use this kind of data to, for example, to define if a client is active or non-active, and so if it's a core client for the bank. And third, we have a lot of them, and it allowed on this project to use deep learning models, which are very big data consumers. And also, it allowed us to use optimization techniques such as stochastic gradient descent with differential privacy. Now I want to give you a little bit of insights on what the data contains. So we have the raw transactions of clients. That's what you see on the right, the top right. Their spendings with credit cards or debit cards. To prepare our data set, we decided to not use merchant names, but use SIC codes instead. SIC codes are simply standard categorization of business activities. We then aggregate all the transactions for a month for each client, and this gives us a vector with SIC codes as its dimensions. And one last insight for you, the vectors are very sparse because, as you can imagine, a client rarely spends his money on all categories in 1 month. I will now let Adrien talk about the models.
So the model we use, first family of generative model we use is variational autoencoder. So basically what an autoencoder will do, it will take some high-dimensional data as input, in our case a transactional profile, and it will try to compress the information into a lower dimension. And then a second network, the decoder network, will take the compressed information and will try to recreate some high-dimensional data which are as close as possible from the input data. In the case of variational autoencoder, The compressed layer is not just a standard layer, but actually this layer would represent mean and standard deviation from a distribution we use to sample some observation from and give those observations to the decoder network. We believe that the use of a variational autoencoder have two main advantages. It allows us to better model data, and also adding some randomness with sampling in the core of our network, it should make it more privacy preserving. Second family of model we use are generative adversarial nets. Those models are really popular and have been having great success in the past, generating some images of faces, but we can also apply them on tabular data such as transactional data. Basically, how it works, you have a first network which is trying to generate some data from noise, and a second network which is trying to distinguish between real and fake data. And both networks are trained once against each other, the generating model trying to foolish the discriminator models and the discriminator model trying to distinguish between real and synthetic data. Something really interesting in the training process is you can use epsilon differential privacy in it. What I mean is by adding some Gaussian noise to the gradient and using the moment and content technique to track the privacy budget, we can guarantee that the stochastic gradient descent process is epsilon differential private. What it means is while we are training our model, we can measure the amount of privacy which is consumed by the training of the model. So if we jump into the results, in order to evaluate models, we look at three main characteristics. The first one is the ability by the model to reproduce some sparse data. Second one is cosine similarity. So cosine similarity would be when you look at the transactional profile as a vector of transaction that will give you information about someone's behavior. We would compare this information from the real data with synthetic data. Second one is Westerstein distance, which would be if we take each category independently. So let's say we look at the spend in the grocery. We will look at how good the model is at reproducing grocery spend with comparing the Westerstein distance between the true and transactional data. So Westerstein distance is for one category, how good the model is, and the cosine similarity is for one transactional profile, how close it is to the real data. So if we look at the result first for the sparsity, we can see that most of the model managed to reproduce sparse data except the differential private conditional GAN. We had some trouble training the conditional GAN with the differential privacy, but we have some ideas in order to improve this in the future. If we look at the Westerstein distance, we can see that the variational autoencoder models provide some great results and really good prediction synthetic data for this. We will look at the result in detail in the next slides. We can see that the DP variational autoencoder perform less good than the one trained without differential privacy. That's something to be expected since we are adding some noise during the training on the gradients. So the performance is not as good as the variational autoencoder, but still the results are really interesting. One of the main drawbacks when we are using the variational autoencoder family models is that the cosine similarity is not that great, which means the models are really good to reproduce some category of data if you take them one at a time. But if you look at the behavior of one client across all of the categories, the variational autoencoder has more difficulties to capture this. Whereas the conditional GAN would provide a better result for the cosine similarity. Where we can see we have 0.34, which is quite good. But the drawback is that the Westerstein distance is less good, and we could even sometimes ending up with some crazy value here, and we will see why in the next slide. So if we have a close look on the synthetic data, here we plot the distribution of log spend for the category of clauses for both the true and the synthetic data. So first thing we can notice is that the model is actually reproducing some sparse data. We can see those huge spike in spent of $0. Maybe the synthetic data are a little bit less sparse than the true data, but still the data produced is really sparse. Second thing that we can notice is even if the model is able to reproduce some zero data and some spans that are different from zero, most of the time we end up with those kind of distribution where the amount of data that is the amount of money spent generated by the model is not big enough compared to the real data. Those data should be more stretched to the right. And lastly, some interesting point, and we weren't expecting this actually. The generative model was also able to generate some more extreme value. What I mean by extreme value is if you look at spent in closes, most of people would spend maybe a couple of $100 monthly in close, but some people or organization may spend much more money, maybe some dozen of thousands of dollars. And the generative adversarial network were quite good at capturing and recreating such observation. One drawback is they were too good and they were producing sometimes some crazy observation with maybe people spending billions of dollars in close, which was not realistic given the data. That's mainly due to the GAN form and the fact that we are training on the log of the data, and when we are detransforming it, it can produce some crazy value. And those crazy value would explain the really large value for the variation distance we see in the previous slide. Now, if we look at the result provided by the variational autoencoder, I would say that the key insights are the same. We can see that the distribution is even better, which makes sense since we have seen that the version distance is much closer. It's also interesting to see that the variational autoencoder also was able to create more extreme values, but without having the same issue as the GAN as creating some crazy values. Lastly, some really interesting point is that our synthetic data was able to conserve some additive property of the original data. What I mean by that is if we create new spending categories that we would call most common, which is the sum of the spend in some of the most common categories. So let's say we would add the spend in grocery, restaurants, pharmacy and drugstore, maybe some other categories closes, and we would create one super category with the spend in all of those categories. We'll see that the distribution of the data between the true data and synthetic data are quite close. And this is really interesting at the bank where typically we would use some super category like this to measure how active a client is with his credit card given the dependency the spend he would do on key categories. So this is really promising result for the bank. In conclusion, we say using deep learning technique, we're able to reproduce some of the dataset main characteristic, and that's really interesting. However, the data generation process is not fully production ready yet due to the training instability, mostly with the GAN, and the fact that we have to craft the result in order to get rid of those two extreme value. The process is not fully applicable. One other thing is we still need to evaluate the privacy of the synthetic data. We can do this with two ways. First is improve the DP training for the GAN mainly. And one way of doing this would be to apply noise only on the discriminator and not on the generator, since the generator doesn't see the real data. And we could also use membership attack to measure the privacy of the synthetic data at posteriori. And I will let Patrick conclude.
Thank you, Adrien. Let's finish by talking about applications in the next 5 years. So our main objective with this project was to bring awareness on the fact that anonymization is not robust, and we shall use privacy-preserving data science instead. We believe this could allow us to lower the risk of data inside the bank, but also facilitate giving access to some information outside the bank, for example, by publishing papers or organizing hackathons. A more far-fetched application would be to have an open marketplace of synthetic data because they would still be embedded with business value. Thank you for listening to us. I hope this was interesting to you. Don't hesitate to contact us for any question.
Hi, everyone. Thank you very much for joining us today at OpenMind's first privacy conference. My name is Karthik Chopra, and today I will be talking to you about secure machine learning practices in the national security sector as the organizations are adopting privacy-preserving machine learning technologies. We will talk about specific use cases, methods, the design of a team, and the approaches that are working inside of these organizations to preserve the privacy of classified and very sensitive data sources. A little bit about myself. My name is Kartik, and I'm a former intelligence officer with almost a decade in national security. Most of my experience has been in deploying multimodal systems to include image, text, audio, and speech in various different parts of the world and environments that allow us to generate better insights about information overseas. A lot of my work has been also to include advising early stage startups and building machine learning teams that incorporate product managers, software engineers, machine learning engineers, and machine learning researchers. The problem in the space for many, many years has been the leaks that the US government has seen on how cybersecurity is being attacked given the kind of data sets that have leaked to the public. Specifically, the breaches inside the Office of Personnel Management, the Snowden leaks, and various insider threat scenarios have shaken up the industry on how do we conduct not only data and code governance, but also model governance inside of these organizations. The OPM breach specifically was a breach that leaked access to various sensitive information of US government staffers and specific PII that was contained in centralized data lakes. The Snowden leaks included various sources and methods that were perceived to be believed by and intercepted by the US government. An insider threat where various data governance procedures and methods were attacked to then retrieve vital classified information by a specific user published in the open internet. To solve and overcome these problems, various organizations are investing billions of dollars in artificial intelligence from the defense and the intelligence communities. Strategic investments are being made in multi-intelligence data platforms that include image, text, audio, speech, geolocation, and various other types of intelligence. And these systems and their distributed natures create very advanced environments for engineers to adapt and build towards. And as these investments are being made in these communities, we are opening our eyes to how do we continue to preserve the privacy of the types of the sensitive information that we're building these systems on. What this is allowing us to do is that it's enabling us for cross-organizational knowledge transfer, where decades ago, things were done on manual labor, where now due to the cloud and on-prem environments, a lot of these organizations are able to communicate through centralized data systems. The reason why we are talking about this now and various specific investments are being made in data privacy is that we are realizing the kind of environment that the US government deals and works in is that software engineers are building technologies where privacy needs to be preserved at all times. which means that given an environment where all of the data you are working with is classified, top secret, secret, and various different kinds of classifications and compartmentalizations, how do we preserve the privacy of these data sets while also adopting to the various new techniques of artificial intelligence to keep up with research? The first step to start a foundational effort in these approaches is to have a team. There's various parts of an engineering team, and what we'll be discussing here is in that approaches that have worked inside US government organizations where the engineers, product managers, UI UX, business development, and customer discovery officers have been able to understand how specific classified data sources need to be handled, how our specific human intelligence, signals intelligence, and geolocation intelligence data is being commingled, and while the commingling is happening, also leaking various sensitivity of the underlying data sets. To start with engineers are often being involved in customer discovery and design and framing meetings where we work with the operators and better understand how the data is being accessed at the edge and then transmitted into an ecosystem where a lot of the analysis needs to happen. The engineers this way adapt to technologies and build cybersecurity systems that are not only robust when it comes to security, but also preserve the privacy of the data that is underlying in these systems. Because of the emerging nature of these technologies, various product managers have traits that enable them to translate classified requirements in very non-sensitive environments. What I mean there is that the ability to work with an engineering team that has the government clearance to learn about specific nuances of that classified data, a product manager translates those requirements to perhaps then an engineering team that doesn't have the government clearance, but needs to decouple the classified data sources and the classified sources and methods to how the product or the machine learning models need to adapt to that new ecosystem. Likewise, with the UI UX teams, user experience for how the operators are deploying this AI technology needs to be translated back to the engineering teams and the product managers, which continues to enable the team at large on how to build a privacy-preserving system. And likewise for business development, which in the government space are individuals that are finding more use cases. They are at the forefront of pitching and better understanding how secure machine learning systems need to be built in various different US government environments, which means the underlying understanding of privacy-preserving technologies to include distributed machine learning, to include differential privacy, need to be translated to executives in a way that solves a solution that that US government entity is trying to build towards. One example to start these initiatives is to begin with an open mind. And what that means is that allowing government organizations and engineers and data science teams to learn more about technologies that are built by OpenMined allows data science and software engineering teams to get quickly started with privacy-preserving machine learning technologies. And organizations, as they're learning more about the research and the software stack that is being published by OpenMined, has now started to prove out specific use cases for how government organizations can conduct privacy-preserving machine learnings in a national security environment. For example, what we have here is a 3 multi-party federated learning system that helps the USA Jobs website to better classify resumes as applicants are applying to work in these 3 specific government organizations as civilians. So the goal here is that as candidates are applying to be a civilian at the Army, at the Air Force, or at the US Navy, candidates' resumes and the privacy of that candidate needs to be preserved as their resumes are going through the recruitment process. The goal for USA Jobs is to build a classifier that better understands the traits of a US Army applicant, a US Navy applicant, and a US Air Force applicant without sharing the data from all the 3 different parties. And what PyGrid and PySift can allow engineers in these ecosystems to start with early on is an architecture that allows the 3 organizations to train a machine learning model on applicants' data in their own environments, but to only share the insights and the model feedback and parameters to the USA Jobs, where many civilians apply to begin with. A traditional process currently is that USA Jobs takes in a civilian's application or a resume, and then communicates asynchronously to US Army, to the Air Force, and the Navy to better understand how that applicant is suited for 3 parties or just one organization. Having a system that better assists recruitment officers to hire individuals that are well-rounded for all 3 of these organizations as civilians allows USA Jobs to create a machine learning classifier that is distributedly learning from the 3 data sets residing in these 3 organizations, while building a better classifier at the edge where the applicants are applying on the USA Jobs website. And using OpenMind's technologies, a proof of concept has been able to show how specific use cases like this can prove to the organizations that without the ability to share the data, they were still able to generate insights and create a classifier that will assist an organization to better learn about applicants coming in and make decisions at the edge. What I would love to open now for is a question and answering, and I thank you for everyone for being here, and I hope everyone is healthy and safe. Thank you very much.
Greetings, everyone. What I'm going to share with you is essentially an outline of the steps that need to happen to bring privacy forward as an asset for your brand. And I'm out here on this highway under construction because what we're talking about here is a journey. It takes a lot of work to get there, but with some commitment and well-pointed effort, you're going to be able to leverage a strong product value proposition with an emphasis on privacy to propel your brand forward in meaningful ways. And because we're out here on this road, I'm going to start with a little story about my first journey. I was born at the end of the baby boom and the beginning of the Xers in December of 1964. Now, for your reference, that's the year 11 BDC. BDC, you know, before desktop computers. The year 12 BDC, my dad bought one of these right off the lot. The 1963 Rambler Ambassador 880. Not exactly a design triumph, but it was the first car I ever rode in. In fact, my earliest vivid memories is in the back seat of that car, which looked pretty much exactly like this. And you may ask, how do I remember what that car looked like so clearly? Well, if you look at the pictures, there's something missing. Seat belts. I crawled, slobbered, and spilled all over that back seat, and I remember jumping on it like a trampoline, looking out the back window and waving at the cars behind as my parents drove around the city, oblivious to what we now see as the insane danger. And looking back on it, it was insane. Death by vehicle numbers between 1964 and 1968, the years I was bouncing around that back seat, were among the highest in history. Today's numbers, even with faster cars on more crowded highways, are about 60% lower. Now, the people who invented seatbelts understood that the cars that they were selling were killing their customers. And eventually a problem like that is going to get noticed. And that is exactly what happened in 1965 when Ralph Nader published this book, Unsafe at Any Speed. Now, most of you are likely too young to have come across it. But it ignited a firestorm that was the catalyst for accountability, new safety standards, testing, and other reforms in the U.S. automotive industry that ended up being rolled into the National Traffic Safety and Motor Vehicle Act. And now, over the last decade, AI has evolved into an unsafe vehicle speeding down the road with its passengers gleefully unaware that they are fundamentally unsafe. Now, 5 to 7 years from now, I think they're going to look back on today and wonder how in the world we existed with the haphazard privacy frameworks and lack of ability to safely access and benefit from meaning and data without compromise. A rough equivalent to the National Traffic and Motor Safety Vehicle Act has been GDPR. It's been a loud wake-up call for a lot of companies who have been playing fast and furious with customer data. GDPR was seen by many as a bad, nasty obstacle. And it was for those exploiting data without regard for the people that it's tied to. But here's what I want you to know. There's a real opportunity right now for those companies willing to go for it, to emerge as leading the new era for care and sensitivity around customer data. Now, if you're attending these sessions, you are a data privacy pioneer. You're already thinking ahead of at least 98% plus of the market about how to care for and protect customers' interests. Now, at the heart of an organization that advocates for privacy is the fundamental belief that customers' interests come first. And that's a really smart place to be. But it seems to be increasingly uncommon, and here's why. There is so much available capital. We're living in a time of practically unlimited funds, relatively speaking anyway. Companies once actually had to live by the metrics of basic unit economics. They had to work to ensure their customers were thriving and happy with their products. But now, we're living in this free money fantasy, and companies' focus is totally fragmented. They have to make sure that they're pleasing investors, media, analysts, regulators, then maybe customers. It's optics over output. And let me tell you, the market's getting really tired of being led down blind alleys lined with fake claims, promises, vaporware, and empty and little regard for any of the fallout. Ever heard of Theranos, anyone? The market's getting tired and wise to the scent of being exploited. We need seatbelts, and the market is starting to demand it. So our agency, Golden Spiral, helps bring B2B SaaS solutions to market. Our team often gets the chance to interview our clients' customers about their needs, and a common thread is emerging. Their customers want to know, how are you going to respect my data? Not just, do you respect my data, but specifically, how are you going to do it? What measures are you putting in place to safeguard my customers as you dive in and operate on my data sets? Because we cannot be compromised. The answers a lot of organizations are able to give to those questions right now are lacking substance. It's an opportunity. So let's explore the outline of those steps that need to happen to bring privacy forward as a brand asset. It's a collection of wisdom and input from Forrester, Serious Decisions, and our team at Golden Spiral. And this is decidedly a condensed flyby of what is unavoidably a deep, involved process. But every step here is critical. Don't be tempted to shortcut the process. Don't do it. Every step is important. Now, the preliminary qualifier before jumping in is that there has to be a DNA belief that doing the right thing for your customers is the best way to go. It's great for business. And as I said earlier, that's no longer a given. James Clear, the author of New York Times bestseller Atomic Habits, recently tweeted, "Businesses succeed when the self-interest of the business is aligned with the self-interest of the customer." So if that's true of your organization, then you can go to the next step. If not, if loyalty in your company goes first to investors or shareholders, then you have to fix that problem before you can move any further. And unfortunately, it's hard to do if you're anywhere other than in the C-suite. Be realistic here. It's really unusual to change the DNA of a company unless you're leading it. It can happen, but it's really, really rare. Okay, so we'll say you're in a customer-first company. Great, it's the right place to be. So let's get to work. Step 1, it's the groundwork. You need to form your team. You need a well-positioned, empowered representative from every critical facet of your org that touches customer data. They need to share your vision for protecting privacy. They need to understand what it can mean for your brand, and then they need to be empowered to take action in their particular sphere. Unity and clarity in this team is essential. Then you want to analyze your competition and your market. You have to understand what your competition is doing and saying about privacy. Now, chances are at this point, they're not saying very much. Very few are. Most of the talk about this right now is from third parties, and they're talking about abuses and infractions that are happening. You also need to have a clear understanding of what your customers know and they don't know, what they care about and what they don't care about. You have a real opportunity here to assert something meaningful that will clearly differentiate you in the market. That is gold from a marketing perspective. You want to know exactly how to do it in a way that builds bridges of understanding and really stands out in the crowd. Then you want to create a charter. This is a document that outlines what privacy ultimately looks like within your organization. It's just a brief. It starts by complimenting the organization on where it is at the moment. And then it outlines the opportunity that exists to bring privacy forward. Then, based on your analysis of the competition and the market, it broadly maps out the plan of where you're going to go to make this happen in the organization. Finally, you want to provide an overview of how you intend to take it to the market. It's important not to get bogged down in the obstacles or restrictions. Keep it focused on the opportunities and the freedom that comes with having systems that support privacy. Then step 2, you need to evangelize this internally. Privacy is not a casual commitment. It has to be a part of your culture, and the whole company needs to understand the priority. Use your charter as the foundation and create a picture of what the market opportunity is and what it's going to require, and ultimately what it will mean for your brand to emerge as a leader in privacy. This is an internal marketing campaign. It shares almost all the attributes of an external campaign. You're driving awareness, you're educating, you're creating momentum and excitement. and you're enlisting people to act because you're going to need their help in the next step. Then step 3, make privacy happen. This is a big lift, no matter what. But if you've done the work of the internal evangelism, this will be much easier. Here's the sequence. Work with your team to do an audit to get a comprehensive picture of how you're handling data. Identify the needs and shortcomings. Then establish new best practices, and once you have that, then enact them. And set a process in place to monitor it all for compliance. It's that easy. Not. I can virtually sense a lot of your eyes rolling out there. I know what I just outlined could take a determined year in some organizations, and it's a really big part of why privacy rarely comes out as a value. But I'm convinced this journey is worth the effort. Now, step 4. Evangelize the problem externally without selling. Right now, your market's likely a mix of awareness of issues surrounding AI and privacy. Get to work leading the conversation. Outline the dangers, the vulnerabilities, and the consequences of reckless behavior in your particular context. Talk about what the future thinking looks like, and help them understand how they need to be seeing the issue in light of what the vanguard of technology is beginning to afford here. You're letting them know that you're thinking about this and you're committed to this cause. It's not selling. You're not talking about your product. You're helping them into a smart, informed perspective of the issues. This can be done through a whole variety of methods. You can sponsor OpenMined, for instance. You can publicize third-party studies and articles. You can create original content explaining how smart organizations are caring for data and how technology is emerging that's going to allow real meaning to come out of data that we can't see. You can even apply your expertise to offer privacy audits for high-level customers and help them see the opportunities in their own organizations. Help your market know how they need to think about privacy. And then step 5, take it to market. Okay, here's what it looks like. Start by formalizing privacy as a value. Declare it as clearly as you can as a part of who you are and how you roll, however that may make sense in your organization. Then, get transparent about it. Lay it all out there. Conspicuously publish exactly how you treat data and the standards and measures you employ to ensure privacy. And then promote it. Create market-focused messages that marry privacy to your value proposition and launch a campaign to let them know the ways you respect, value, and aggressively promote privacy. Then, if you have the guts, challenge your industry to join you on the vanguard. You're already leading. You're ahead of them. Publicly challenge your competition to join you. It'll demonstrate your leadership. So, all of that is the fun part. But there's one more essential step. You have to have a plan for when something goes wrong. Chances are it will. And smart companies have a proactive plan that understands the regulatory and reporting rules, knows who needs to communicate what to who, and what you're prepared to do to take responsibility and work to restore trust. No one likes to think about this stuff. But the best thing you can do is react quickly, honestly, and thoroughly when the trust airbag doesn't inflate upon impact. Now, that's a ton, and it's not for the faint of heart, but I'm going to say it again, there's real opportunity here. By virtue of the fact that you are tuned into this conference, you're ahead of the herd. Starting this work now is likely going to mean that you're going to stay there. You don't have to go it alone. There's help out there. As I mentioned at the start, the team at Forrester and Sirius have done some great work here, and if you're in the B2B sphere, our team at Golden Spiral knows this realm, and we can help you create and carry out a plan. My personal email is john@goldenspiralmarketing.com. Please feel free to contact me if there's anything here that you would like to discuss further. I just want to say, I really appreciate your time today. I'm especially grateful for everything that you're doing to advocate for a safer, more respectful, and smarter world. Enjoy the journey and stay safe.
Hey everybody, I'm Nick Elledge, one of the co-founders of Data Fleets. Thanks for taking time out of your day to chat about getting privacy-enhancing technologies out of the lab and into real production use cases, something that's very near and dear to my heart. And I hope by sharing our experience here at PryCon, we're able to get more and more impact out in the world. So, starting right out of the gate, what are the 6 things that enterprises really care about when they're evaluating privacy enhancing technologies? I'll get into that, but first you have to understand a little bit about the types of people that you're going to run into when you're trying to either sell or market or otherwise get these into use. Three kinds of people. First are people who have never heard of the technology. So you'll say homomorphic encryption and they'll look at you like you are speaking a foreign language. The second is that they have heard of it, but they haven't heard good things. So there's some disillusionment. They've heard it impacts the analytics quality. They've heard it's slow, it doesn't scale. Somehow they believe this just isn't going to work. They're skeptical. And the final group are those who are trying it in earnest by themselves in that moment already and are recognizing that it's pretty difficult to implement yourself for the first time. And so with that context, depending on who you're running into, there are 6 things that they're really focused on. So first is speed. Second is simplicity. Third is the analytics utility. Fourth is multi-party capabilities. Fifth is privacy. And then finally is security. So I'll run through some explanations and examples of what each of these really represent. So first is speed. Speed is fairly straightforward. It's something that you can benchmark with a certain amount of compute power, being able to achieve, this model trained in 17 minutes. And if your result is this model is going to take 3 years to train, then you have a big problem. And certain privacy-enhancing technologies, specifically those with encryption, sometimes slow things down a lot. So you have to make sure that the amount of data that you're dealing with is fit for that particular use case. The second is simplicity. So how many extra trainings, extra pieces of process do I have to put into my organization in order to really make this work? The third is utility. Is this going to impact and specifically degrade the quality of my analytics? Am I going to get back garbage results from this, or is it going to be the real results? Fourth, multi-party capabilities. A lot of privacy and private data exchanges involve multiple parties being involved, and not every technology and not every system enables those exchanges to happen end to end. Fifth is the privacy guarantees that you're able to afford. So depending on the situation, how sensitive the data is, how much you trust the actors who are going to be accessing it, you'll have different configurations for privacy. But being able to prove, not only mathematically, but legally, that you are compliant on privacy regulations is critical. And sixth is security. One area that's pretty critical here, but sometimes uncomfortable to broach, is that 30% of data breaches come from insiders, someone who has a bad intention or was just going through a really rough period and decided to take it out on your organization. And those security breaches can be reduced if you have privacy enhancing technologies in place, if people aren't accessing the real and sensitive underlying data. So being able to prove that you're elevating the game on security above the status quo is a sixth thing that enterprises do care about. So hopefully by sharing that framework gives you a sense of, when I'm approaching someone, whether they've never heard of it, whether they've heard bad things, or whether they're trying it now for the first time, you're able to walk through that framework and be able to prove to them where the trade-offs are in your stack. There are no silver bullets. within privacy enhancing technologies. So being able to show them why this is fit for the use case that they want using that framework hopefully is helpful. But that brings me to a second and larger point, which is that the technology is only part of it. A chief analytics officer at a major financial institution shared with us recently that he thinks about three things. First is technology, but second is people, and third is processes. And that's core to his job. Solving the technology problem is only a piece of it. And the example I can share here is federated learning. Being able to ship a model out to where data sets reside without having to aggregate those data sets into a data lake or some other centralized repository, without having to make copies of that sensitive information, have all the redundancies in place, is a paradigm shift. The technology may be ready, but is that company ready for the processes and the people implications that's going to happen to that IT organization within that enterprise? These are the considerations that I think we should be having when we're going to really deploy these, and we want to see impact and value coming out of that. So we've covered the 6 things to be able to benchmark yourself against different personas or people who might be encountering your technology, and then 3 things that analytics officers and IT organizations are thinking about. I think it'd be useful to share 2 use cases that we at Data Fleets are working on, one in federated learning in financial crime, and one in differential privacy with healthcare patient records, maybe illustrate some of the challenges that we've encountered, and maybe you can work with us and help overcome. So the first has to do with federated learning for financial crime. I believe this is an incredible use case. Security collaboration, fraud detection collaboration, the incentives align so beautifully for multiple institutions to share a single model, because none of them can see the full picture. None of them have all the transaction data. None of them are able to see the full elephant, if you will. So the sum is truly greater than the parts. What's the challenge? Well, I believe the biggest challenge in that use case is being able to prove to every single endpoint that their data is being treated in the right way, that it is secure, that it is private, and that they maintain control over it. Now, why is that important? Because those organizations, whether it's banks, asset managers, hedge funds, etc., are worried that their information may be exposed to others. These are competitors of theirs at the end of the day. They also are worried about the regulatory challenges. Are they breaking the law, or are they going to get cracked down on by financial regulators for engaging in this type of fraud detection collaboration? Being able to get stamps of approval from the legal community on those mathematically proven techniques is important, and something that will help move that use case forward. So a second example, differential privacy for patient records. This is not a federated use case. This is just trying to take patient records for healthcare and make them available to academic researchers for hypothesis testing in a differentially private manner. It's a remote execution use case. What are the challenges? Well, there are 2 big ones. First is an education component. What is your privacy budget? What is an epsilon parameter? There are a lot of insider terms that you have to come up to speed on within differential privacy to be able to use it effectively. And the second really is HIPAA certification. So how do we map HIPAA's guidelines around safe harbor and around expert determination to the mathematical guarantees afforded by differential privacy? This is work that's ongoing by a number of communities and scholars, and I believe that the results that are coming out, at least in the last 12 months, have been stellar, but something that would be solved more quickly if we had some sort of gold standard to be able to point to. And one of the final challenges is being able to demonstrate the analytics quality is the same or even better in this use case than having access to the raw data. Or in certain circumstances, being able to allow access to the raw data under the right conditions. So again, that is absolutely critical to making this use case work. So those are some use cases. Those are a framework for thinking about deploying these for enterprises and how they're being evaluated. I'd love to just close out by sharing a little bit more about my background, how I came into this, and what I'm hoping to be able to achieve out of our work with OpenMined and with data fleets. So a lot of my background was in international development and human rights. And I encountered a number of situations where data privacy kept us from being able to achieve outcomes that we wanted, that we felt like were going to have an impact in the world. So I remember it was almost 10 years ago now, working in a country in East Africa, trying to craft for them a strategy for climate change mitigation, because climate and weather pattern changes dramatically impact the rainfall for their hydropower and obviously for agriculture and for drinking water. What I didn't expect was that historical rainfall patterns over the last 30 years, which we needed to train that model, were sensitive. That country didn't want to expose that they had actually had droughts that they had not publicly announced to the international community and to the press. And we ended up getting only a redacted and partial version of that data set. And I wish that we had some sort of privacy guarantees on that model training to be able to access the full data set. We encountered this again when we were doing labor work for a Middle Eastern government. They wanted to be able to reduce unemployment in their country. A lot of young people were unemployed and struggling, and in order to help, we needed to get access to the labor data set. That included gender, that included the number of migrants and people from international backgrounds within that community. It included the wages of those people. And that was considered too sensitive to give us access to. And in the end, ended up making it so we couldn't move forward with that project. Those are two examples of things that I've run into. I'm sure you have your own examples and motivations, but I'm hopeful that we're going to be able to create a world where statistics organizations and economic decisions and international development is able to access those kinds of data sets easily and with the security and privacy guarantees that are afforded by these technologies. Thank you so much to Andrew Trask for allowing us to sponsor this year's conference and allowing us to speak. We look forward to many more years of collaboration. And thank you for taking the time. Please feel free to reach out. We're at Data Fleets on Twitter, and I'm Nick at datafleets.com. Thanks so much. Have a great rest of your conference.
Well, very sadly, that is our last session of PrideCon 2020. I hope you've enjoyed all the speakers we've gotten to hear from, that you've been able to engage in Slack and gather, and to make new friends, and now have a better picture of how you can fit into the privacy community. Before we close, I'd like to say that this conference was organized not by paid individuals or any form of professional, but by volunteers who together spent hundreds of hours working on every detail you've seen in the last 2 days. Everyone who is helping to organize this conference is doing so because we believe in the future that privacy-preserving technologies can bring. And we feel that putting on community events like this one are essential to helping us organize to get there. And so to help us say thank you, I would like to ask you to do one more thing. I want you to, if you remember in our opening session, we did the sort of B letter as like an upvote. For each group and individual that I'm about to thank, I ask that you would really bring out the B's and help me give what would be in person a huge round of applause for all the people who supported the development of this conference. So first and foremost, obviously our speakers. Couldn't have a conference without them. And from the stories that I've heard, I mean, speakers, especially ones that were putting together videos ahead of time, worked so hard to make the talks. I mean, I heard of multiple speakers who were re-recording their session 5, 10, even 15 times just to get the perfect message that is as clear and crisp as possible. And so when you think about the combined amount of effort across all 60 people to create this much content of this high quality, it's really, we owe this conference to their willingness to volunteer, to lower the barrier to entry for us to learn these things. So huge thank you to all of our speakers. And secondly, to all of our sponsors. Without your financial support, OpenMined would not be able to do full-time development and provide events like this one and educational content like our courses, tutorials, and blogs. Thank you so much for all of your support. And to everyone in the audience, if you're looking for a privacy startup or enterprise to work for, or to have as a customer, or just looking to fill up your social media feed with more privacy awesomeness, please do consider our sponsors, as they literally keep the lights on for all of our paid contributors. And finally, for the conference organizing team, in no particular order, Bennett, Farkas, and Kyoko, OpenMind's brand and a huge number of branded assets came from Bennett, Kyoko, and the design team. Everything you saw on social media, all the slides between talks, the polished headshots both on social media and on the website design, even the template for a lot of the slide decks that you saw within the talk were provided thanks to the talent of Bennett and Kyoko and the design team. So huge thank you. The visual design of the conference was absolutely beautiful, and it's all thanks to your expertise and ability, as well as your willingness to lend that to this volunteer initiative. Second is Madeline Mamliano, who leads our social media team, and for the last several months has been scheduling and pushing out our social media content, and especially for his deep expertise in live video streaming, coming through in the clutch to save our bacon yesterday when our streaming service provider lost their internet connection. Huge thank you to Madeline. You literally kept this conference going all the way to the end. Next, I'd like to thank Kelly Trask, who drove the marketing strategy for the conference, leading to over 2,500 registrations for the conference and 350 concurrent live streams, even though our conference spans the entire world of time zones. Kelly optimized our messaging, coordinated assets, and created content featuring each speaker's unique story in our conference social media campaign. Thank you so much, Kelly. Next, I'd like to thank Amber, who put together our Gather Town and collated videos from all of our different teams to put together this morning's community session. She also has to put up with me on a daily basis, which has its own challenges. Thank you, Amber. Patrick Kaysen, who developed the website with a hugely fast turnaround time in less than, I think, 48 hours. And since then, he's provided endless IT support across the needs of the conference. Thank you, Patrick. Next, I'd like to thank Shaista, who emailed, managed, and collected the information for over 60 speakers attending the conference. She's basically lived on email for the last few months, dealing with every possible hurdle you can imagine. A huge thank you to Shaista. Next is Emma Bloomkey, Jess Sachin, and the whole partnerships team, who worked with all the sponsors and partners to help facilitate many of the talks that you saw today and yesterday, to cover the costs associated with the conference and support additional developer grants within the community through our bronze, silver, and gold sponsorships. This required endless Zoom calls in the weeks leading up to the conference with all of our fantastic partners, and we're hugely grateful for their work. And last, but certainly not least, Chris Briggs, the lead organizer for the conference, whose determination, grit, persistence, patience, and an insane amount of hard work made this conference happen. In no uncertain terms, PryCon 2020 happened because Chris Briggs agreed to put it on only 3 months ago. And it has been on his shoulders for all this time, involving many late nights, editing last-minute video additions and corrections, and in general, a huge amount of care for privacy, for the audience, and patience with the rest of us. A huge thank you to Chris Briggs. And to that end, if you think you might be interested in joining amazing people like Chris in planning events, writing code, or teaching concepts in blog posts and videos, you should consider joining OpenMined. You can do so by looking at the open volunteer positions page at placements.openmind.org. And with that, I thank you for coming to PryCon. I thank you for joining us on our mission to change the world for privacy, and I leave you with a final word. Let's solve privacy.